What if the universe's darkest secrets were born in its first moments? Think about that just an instant after everything began. Hidden forces may have already been weaving mysteries into the very fabric of space and time. There are places in our cosmos where gravity becomes so powerful that not even light can escape. And though we've detected black holes formed by collapsing stars, there may be another kind far older, far stranger, and possibly holding answers to questions we haven't even fully asked yet. These are known as primordial black holes, and if they exist, they could change everything we know about the universe. Imagine a reality so dense and hot that matter and energy were almost indistinguishable, a seething chaos from which the first structures of the cosmos began to emerge. In that newborn universe, tiny fluctuations in density might have given birth to black holes not from dying stars, but from the raw energy of creation itself. These primordial black holes could be hiding in plain sight today, invisible, ancient, and carrying clues about the earliest moments of existence. Some might be as small as an atom, others as massive as planets, and their stories could reveal how galaxies formed, what dark matter really is, and even whether our universe is one of many. This journey is about to take us through 30 incredible theories about these elusive cosmic ghosts, ideas that stretch the imagination and challenge the foundations of modern physics. We'll explore how they might solve long-standing mysteries, influence the structure of everything we see, and perhaps even shape the fate of the cosmos itself. Prepare to dive into a world where time, space, and possibility bend in ways that defy easy understanding. Whether you're new to these concepts or have been fascinated by them for years, what lies ahead will invite you to see the universe and our place in it in a completely new light. To understand where these enigmatic objects might come from, we need to rewind the cosmic clock almost all the way back to the very beginning. In the first fleeting fractions of a second after the Big Bang, the entire universe was an unimaginably hot, dense, and rapidly expanding soup of fundamental particles and energy. It was a place of incredible chaos and pressure, where the laws of physics as we know them were pushed to their absolute limits. Within this seething primordial plasma, the universe wasn't perfectly smooth. Thanks to the weird rules of quantum mechanics, tiny, random fluctuations in density were popping in and out of existence everywhere. Think of it like the surface of a boiling pot of water, with bubbles constantly forming and collapsing, but on a cosmic scale. Most of these fluctuations would have instantly smoothed themselves out, vanished without a trace in the furious expansion. But for some, the conditions were just right for something extraordinary to happen. In regions where the fluctuation was particularly intense, creating a knot of matter and energy that was significantly denser than its surroundings, gravity could have taken over in a dramatic fashion. The outward pressure from the hot plasma and the rapid expansion of the universe were fighting against the inward pull of gravity. In these ultra-dense pockets, gravity won. This is the core idea behind our first theory, that these primordial black holes are direct relics of the Big Bang, formed when those extreme density fluctuations underwent gravitational collapse. It's a process fundamentally different from how the black holes we're more familiar with are born. Stellar black holes are the end result of a star's life cycle, when a massive star runs out of fuel and its core collapses under its own immense weight. That process takes millions of years and requires a star many times more massive than our Sun. Primordial black hole formation, by contrast, would have been almost instantaneous. It wasn't about a star dying, it was about the universe itself giving birth to black holes directly from its raw, explosive energy. And because this could happen across a vast spectrum of density sizes, these objects wouldn't all have the same mass. A particularly large fluctuation could have collapsed into a black hole with the mass of a planet, while a smaller one might have created a black hole no heavier than a mountain yet smaller than an atom. This alone makes them vastly different from their stellar cousins and opens up a world of fascinating possibilities for what might be hiding in the darkness. Now, the fascinating part is that not all density fluctuations are created equal. The specific mechanism thought to create these initial wrinkles in spacetime is cosmic inflation, that brief period of exponential expansion in the universe's very first moments. It's during inflation that quantum fluctuations, tiny ripples at the smallest scales, get stretched to astronomical sizes, becoming the seeds for all future structure, including galaxies and potentially these primordial black holes. The scale of these stretched fluctuations determines everything. A larger region of space that collapses could form a black hole with the mass of an asteroid, while a smaller, more intense knot could create one with the mass of a mountain, yet compressed into a space far smaller than a single proton. This leads us directly to the Kerr-Hawking model, a foundational idea in this field. Physicists Bernard Kerr and Stephen Hawking calculated that for a region to collapse into a primordial black hole, its density contrast, how much denser it was than its surroundings, had to be significant. We're talking about a fluctuation on the order of roughly half the critical density or more. It couldn't be just a tiny bump, it needed to be a truly massive spike. What's incredible is that the mass of the resulting black hole is intrinsically linked to the cosmic time at which it formed. A black hole born when the universe was just 1 second old would have a mass roughly equal to that of a small planet. But if it formed much earlier, say at 100,000th of a second after the Big Bang, its mass could be 1 billion times less, perhaps no more than 1 billion metric tons. That's the mass of a small mountain squeezed into a size smaller than an atomic nucleus. But density perturbations from inflation aren't the only game in town. Another compelling theory involves cosmological phase transitions. Think of the early universe cooling down much like steam condensing into water. As it expanded and cooled, it may have undergone sudden, dramatic shifts in state. One popular idea is that of a first-order phase transition, where bubbles of the new, lower energy phase spontaneously form and begin expanding at nearly the speed of light. When these incredibly energetic bubbles collide, they can create a shock wave of density so intense that it triggers the gravitational collapse of a region of space, instantly forming a primordial black hole. This process could naturally produce black holes within a very specific mass range, offering a potential target for astronomers to search for. Furthermore, there's the concept of the collapse of horizon-sized regions. In the very early universe, the cosmic horizon, the maximum distance light could have traveled since the Big Bang, was incredibly small. If an entire region, one horizon volume across, somehow became overdense, the entire patch could find itself inside its own Schwarzschild radius, inevitably becoming a black hole. The mass of that black hole would be proportional to the mass contained within that horizon volume at the moment of its formation, which again ties its properties directly to the age of the universe when it was born. This creates a spectrum of possibilities, from black holes so light they could potentially evaporate via Hawking radiation to ones so massive they could be the hidden anchors of entire galaxies. This brings us to one of the most profound and compelling ideas in modern cosmology, the possibility that these ancient objects are the invisible stuff holding our universe together. For decades, astronomers have known that something is missing. When they measure how fast stars orbit the center of their galaxies, they find a puzzling discrepancy. The visible matter, all the stars, gas, and dust we can see, simply doesn't provide enough gravitational pull to keep those stars from flying off into intergalactic space. It's as if every galaxy is wrapped in an immense invisible halo of mass, a substance that doesn't emit, absorb, or reflect light. We call this mysterious substance dark matter, and it makes up about 85% of all the matter in the universe. But what is it? The leading hypothesis for years has been that dark matter is made of some exotic, yet to be discovered particle like a WIMP, a weakly interacting massive particle. Giant detectors buried deep underground have been searching for signs of these elusive particles for years, but so far they've found nothing. This lack of evidence has led many scientists to re-examine an older, bolder idea. That dark matter isn't a sea of tiny particles at all, but a population of massive, compact objects. Primordial black holes born in the first second of the universe are a perfect candidate. They are, by their very nature, dark, and they have mass, meaning they exert a powerful gravitational influence. If vast numbers of these primordial black holes were strewn throughout the halos of galaxies, their collective gravity would perfectly explain the rotation curves we observe. They would provide the extra tug needed to keep stars orbiting at high speeds without being flung away. This idea elegantly solves the puzzle without requiring any new physics beyond Einstein's theory of gravity and the established principles of the Big Bang. It's a beautifully simple proposition. The dark matter we've been hunting for decades might not be a mysterious particle, but rather a cosmic fossil from the dawn of time. Of course, a theory this grand must withstand serious scrutiny, and it all comes down to numbers and mass. If primordial black holes are to be the dark matter, there must be enough of them with the right mass to account for all that missing gravitational pull. This is where the concept of the mass window becomes critical. Through decades of observation, astronomers have been able to rule out vast swaths of possible masses for a primordial black hole dark matter candidate. One of the most powerful tools in this search is called microlensing. The principle is brilliant in its simplicity. If a primordial black hole were to pass directly between Earth and a distant star, its gravity would act like a lens, bending the light from that star and causing it to temporarily brighten. By monitoring millions of stars for these characteristic flashes, surveys like the optical gravitational lensing experiment and the Subaru telescope's hyper-subprime CAM have placed tight constraints on how many planet-sized or asteroid-sized black holes could be lurking in our galactic halo. They've largely ruled out the possibility that black holes with masses between 1/10 of the Moon's mass and about 10 times the mass of Jupiter could make up all of dark matter. There simply aren't enough of these lensing events happening. On the other end of the scale, data from the cosmic microwave background, the afterglow of the Big Bang, provides another crucial test. If too many primordial black holes formed in the early universe, their accretion of matter would have pumped extra energy into the primordial gas, leaving a distinct imprint on the CMB's temperature and polarization patterns. The Planck satellite's exquisite measurements have effectively ruled out black holes heavier than a few hundred solar masses from being the primary component of dark matter. So where does that leave us, surprisingly, with two tantalizingly open windows? The first is for very low masses, often called the asteroid mass window. This covers black holes with masses comparable to a large asteroid, somewhere between 1 billion and 1 trillion metric tons. These would be minuscule in size, smaller than a proton, but potentially incredibly numerous. The second open window is for larger objects in the so-called stellar mass range of between 1 and 100 solar masses. This is particularly fascinating because it overlaps with the masses of the black holes detected by LIGO and Virgo through gravitational waves. The discovery of these merging black holes, some of which were surprisingly heavy, reignited the debate, suggesting a primordial origin for at least some of them could be possible. If even a fraction of the dark matter is made of objects in these mass ranges, it would fundamentally reshape our understanding of the cosmos's makeup, suggesting that the answers to our biggest questions have been hiding in black holes all along. Beyond the realm of dark matter, these ancient objects might be hiding much closer to home within our own solar system. For years, astronomers have been puzzled by the strange orbital patterns of a group of small, icy bodies in the distant Kuiper belt, far beyond the orbit of Neptune. These objects have highly elliptical orbits that are clustered together in a way that seems to defy the gravitational influence of the known planets. The most compelling explanation put forward is that an as yet undiscovered world, often dubbed Planet 9, is shepherding them into these peculiar paths through its persistent gravitational tug. This hypothetical planet is estimated to be about 5 to 10 times the mass of Earth, orbiting the Sun on a wildly elongated path that takes between 10 and 20,000 years to complete. But what if this isn't a planet at all? An equally fascinating, though far more exotic, theory suggests that the gravitational culprit isn't a frozen world but a primordial black hole of roughly Earth mass. This would be a relatively small black hole with an event horizon no wider than a grapefruit, yet possessing the gravitational power of an entire planet. Its influence on the distant Kuiper belt would be identical to that of a planet. Gravity doesn't care if the mass is made of rock or is compressed into a singularity. This idea transforms the search for Planet 9 from a hunt for a faint, reflective object into a chase for something utterly dark and invisible. How could we possibly detect such a minuscule, black object in the vast expanse of the outer solar system? Astronomers have devised some incredibly clever methods that lean into its unique nature. One approach involves looking not for the black hole itself, but for the effects of its proposed dark matter halo. According to some models, a primordial black hole could have a dense halo of dark matter particles trapped around it by its intense gravity. If certain theoretical dark matter particles are their own antiparticles, then where these particles meet, they could annihilate each other, releasing a telltale flash of gamma rays. Powerful space telescopes like the Fermi Gamma Ray Space Telescope could potentially detect this faint, steady signal of annihilation radiation, pinpointing the location of this dark traveler. Another detection method relies on the same gravitational lensing techniques used to study distant galaxies, but applied within our solar system. If this primordial black hole were to pass in front of a background star, its gravity would warp space-time and cause the star to momentarily brighten. A dedicated time domain survey, meticulously monitoring the brightness of millions of stars, could catch this fleeting microlensing event. Furthermore, a mission like the upcoming Legacy Survey of Space and Time at the Vera C. Rubin Observatory, with its unprecedented ability to scan the entire visible sky every few nights, would be perfectly suited to catching such a rare and subtle signal, potentially confirming the existence of this ghostly solar system object. The implications of finding a primordial black hole in our own cosmic backyard would be nothing short of revolutionary. It would provide the first direct evidence for these theoretical objects, offering a tangible relic from the universe's first second for us to study. Its presence would suggest that the early universe was capable of producing density fluctuations on a scale that could create Earth mass black holes, informing our models of inflation and quantum genesis. More than just solving the mystery of the Kuiper belt's architecture, it would open a direct window into the most extreme physics of the cosmos, right here in our own celestial neighborhood. While black holes are famously known for their gravitational grip, from which nothing can escape, Stephen Hawking's groundbreaking work revealed they are not entirely black after all. He proposed a stunning mechanism by which black holes could slowly lose mass and eventually vanish in a spectacular burst of energy. This process, now known as Hawking radiation, becomes particularly dramatic when applied to the smallest primordial black holes. It suggests that the universe could be filled with the faint, final whispers of these ancient objects dying. The entire phenomenon hinges on a subtle and bizarre consequence of quantum mechanics, the idea that empty space is not truly empty. What we perceive as a vacuum is actually a seething foam of virtual particles. These are particle-antiparticle pairs that spontaneously pop into existence using borrowed energy from the universe, only to annihilate each other and vanish back into the void an instant later, repaying their energy debt. This constant, frantic activity is happening everywhere all the time. Now, imagine this quantum frenzy occurring right at the very boundary of a black hole's event horizon. If one of these virtual particle pairs appears right at the edge, something extraordinary can happen. Before the pair can annihilate, the immense gravity of the black hole might pull one particle in while its partner escapes into space. From an outside perspective, it looks as if the black hole has just emitted a particle. The particle that falls in has negative energy, and in order to balance the books, the black hole itself loses a tiny amount of mass. This is Hawking radiation, a slow, steady trickle of particles leaking out from a black hole, causing it to evaporate. The rate of this evaporation is inversely proportional to the black hole's mass. For a stellar mass or supermassive black hole, this process is utterly negligible. The energy they absorb from the cosmic microwave background is far greater than the paltry amount they radiate away. They are effectively immortal on timescales longer than the current age of the universe, but for a small primordial black hole, the story is completely different. A black hole with the mass of a small asteroid compressed into a space smaller than a proton has a much smaller event horizon and a much higher temperature. According to Hawking's calculations, the smaller the black hole, the hotter it glows with this radiation, and the faster it evaporates. This leads to a fascinating and explosive timeline. A primordial black hole with a mass of about 1 billion metric tons would have a lifetime roughly equal to the current age of the universe, 13.8 billion years. This means that any such black holes formed in the Big Bang would be reaching the end of their lives right now all across the cosmos, and their deaths would not be quiet affairs. As a black hole evaporates, it doesn't just fade away, it accelerates. In its final second of existence, after sipping away mass for billions of years, the black hole's temperature soars to incredible heights, and it releases the entirety of its remaining mass energy in a tremendous burst of high-energy radiation, equivalent to the detonation of 1,000,001 megaton nuclear bombs. This presents a tantalizing possibility for astronomers. We might be able to witness the death throes of these primordial objects. The final flash would primarily manifest as a short, sharp burst of gamma rays. Our satellites like NASA, a Fermi Gamma Ray Space Telescope, are constantly monitoring the sky for such events. While most gamma-ray bursts are explained by the collapse of massive stars or the mergers of neutron stars, a small fraction have unusual properties that don't quite fit these models. These could potentially be the signature of an evaporating primordial black hole. The telltale sign would be a burst that seems to come from nowhere, with no associated galaxy or prior stellar activity, and with a very specific energy signature. Beyond gamma rays, some models suggest the evaporating black hole could also produce a brief, intense flash of radio waves. As the final burst of particles plows into the interstellar medium, it could create a shock wave detectable by radio telescopes. Searching for these unique signals is like scanning the sky for the last breaths of cosmic ghosts. Finding even one would be a monumental discovery, providing direct proof for both Hawking's brilliant theory and the existence of primordial black holes, while simultaneously giving us a front-row seat to some of the most extreme physics in the universe. These ancient gravitational anchors could have played a far more active role in shaping the cosmos than we ever imagined, potentially serving as the very foundations upon which galaxies were built. In the early universe, after the initial fireball of the Big Bang cooled into a dark, expanding sea of hydrogen and helium gas, the first structures had to form from somewhere. The prevailing theory points to dark matter, which first clumped together into vast halos, whose gravity then drew in the ordinary gas that eventually sparked into stars and galaxies. But this process, driven by cold, collisionless dark matter particles, takes time. There's a problem, however. Our telescopes have revealed fully formed galaxies and incredibly bright quasars powered by supermassive black holes when the universe was less than 1 billion years old. How did they assemble so quickly? This is where primordial black holes offer a compelling and elegant solution. Imagine if, scattered throughout the infant cosmos, there were already pockets of immense density. black holes with masses ranging from a few times that of our Sun to many thousands of times greater. These objects wouldn't just sit there, their powerful gravity would act as natural catalysts for growth. A region of space containing one of these primordial black holes would have a huge head start. Ordinary matter, gas and dust would feel its pull and begin cascading inward much faster than it would around a faint, diffuse clump of dark matter. This rapid accretion could jumpstart the birth of the first stars and the assembly of the first protogalaxies, shaving precious hundreds of millions of years off the timeline of cosmic structure formation. The most stunning evidence for this need for a jumpstart comes from the most distant quasars we observe. These are the dazzlingly bright cores of ancient galaxies, powered by supermassive black holes that have swallowed vast quantities of gas. We now see quasars with black holes weighing over 1 billion solar masses, shining forth from an era when the universe was just 600 million years old. For a black hole to grow that massive that fast through standard accretion physics is a tremendous challenge. It's like finding a fully grown redwood tree in a forest that was only seeded a year ago. The growth process seems to demand a massive seed to begin with, something far larger than the black hole remnant left behind by a single dying star. A primordial black hole formed with a mass of 10,000 or even 100,000 suns right from the outset provides that perfect seed. It wouldn't need to start from scratch. It would already be a gravitational giant in a young universe, immediately beginning to feast on the abundant gas around it. This ready-made anchor could accumulate mass at a phenomenal rate, quickly reaching the staggering sizes we observe in those early quasars. In this scenario, the supermassive black holes we find at the hearts of nearly every large galaxy today, including our own Milky Way, might not have grown slowly over time from small beginnings. Instead, their origins could trace back directly to these primordial giants, around which entire galaxies then coalesced. This idea flips the standard story of galaxy formation on its head. We often think of galaxies forming first, with black holes emerging later within them. But what if it was the other way around? What if the primordial black holes came first, and their immense gravitational wells dictated where the first galaxies would bloom? This would mean that the distribution of galaxies across the universe today, the great cosmic web of clusters and filaments, might actually be a ghostly map tracing the positions of those initial density fluctuations from the Big Bang. The largest structures in the cosmos could be built upon a framework of invisible, ancient holes in spacetime, a hidden architecture that has guided the evolution of everything we see. The quest to unite Einstein's theory of gravity with the bizarre rules of quantum mechanics stands as one of the greatest challenges in all of physics. These two pillars of modern science are incredibly successful in their own domains. General relativity describes the cosmos on the largest scales, while quantum mechanics governs the world of the tiny. Yet where they meet, at the center of a black hole or at the very beginning of the Big Bang, our current understanding breaks down completely into mathematical nonsense. We need a theory of quantum gravity to see into these ultimate extremes, but testing such a theory has always seemed nearly impossible, requiring energy levels and conditions we could never hope to recreate. This is where the tiniest primordial black holes could offer a truly extraordinary opportunity. Because they evaporate, they naturally create the very conditions physicists are desperate to study, providing a potential window into the quantum nature of spacetime itself. As a primordial black hole nears the end of its life through Hawking radiation, its mass plummets while its temperature soars exponentially. In its final moments, it is no longer a classical object described solely by gravity. It becomes a blazing hot quantum system, a place where the warping of spacetime is so intense and the particles being emitted are so energetic that both general relativity and quantum field theory are essential to describe what's happening. This endpoint of evaporation is a natural laboratory for quantum gravity, a unique environment where the fundamental fabric of the universe might reveal its deepest secrets. We cannot build a particle accelerator powerful enough to probe these energies, but the universe might have already created countless natural experiments for us to observe. Different candidate theories for quantum gravity, such as string theory or loop quantum gravity, make distinct predictions about how a black hole's final evaporation might appear. Would the process be truly explosive and complete, as Hawking initially suggested, or would it leave behind a stable, microscopic remnant, a kind of Planck mass fossil that contains the information of everything that ever fell into the black hole? The way information escapes a dying black hole is a central puzzle known as the black hole information paradox. If information is truly lost forever, it violates a core tenet of quantum mechanics. Observing the precise spectrum of particles and radiation emitted in the last second of a primordial black hole's life could provide the data needed to see which theory, if any, correctly resolves this paradox. The signature of this event would be unlike any other known astrophysical transient. It wouldn't be the chaotic collapse of a star or the violent merger of two neutron stars. Instead, it would be a very specific, very rapid burst of high-energy particles. The energy distribution of the gamma rays in that final flash could carry an imprint of the underlying quantum structure of spacetime. It might show a subtle deviation from the thermal spectrum Hawking predicted, a telltale sign that new physics is at play. Some models even suggest that the evaporation could produce a short burst of highly energetic electrons and positrons, or a specific ratio of different particle types, acting like a fingerprint for the theory of everything. Discovering and analyzing such an event would be the astronomical equivalent of finding the Rosetta Stone for fundamental physics. It would transform quantum gravity from a purely theoretical, almost philosophical pursuit into an observational science. By studying the death of these ancient cosmic objects, we wouldn't just be confirming their existence. We would be directly probing the unified laws that govern reality at its most fundamental level, gaining insights into the nature of existence that are completely inaccessible anywhere else in the universe. One of the most profound ways to think about primordial black holes is not just as cosmic oddities, but as potential relics from the universe's very first explosive growth spurt, a period known as cosmic inflation. If we could somehow detect and measure these ancient objects, we might be holding a direct fossilized record of the physics that operated at energies 1 trillion times higher than what the most powerful particle colliders can ever hope to achieve. The key lies in connecting their formation to the specific models of inflation that predict a dramatically amplified power spectrum at certain scales. To understand this, picture the inflationary field, often called the inflaton, as a ball slowly rolling down a hill in an abstract landscape of energy. As it rolls, it drives the incredible exponential expansion of space. For most inflation models, this roll is smooth and steady, producing the nearly scale invariant spectrum of density fluctuations that we see imprinted in the cosmic microwave background. These are the tiny seeds that eventually grew into galaxies and clusters. But what if the ball didn't just roll smoothly? What if the hill had a sudden cliff, a bump, or a plateau? These features in the inflationary potential can cause the ball to slow down dramatically or even briefly pause, and this has a profound effect on the density fluctuations being generated. When the inflaton field slows down, it amplifies the quantum fluctuations. It's like a cosmic microphone turning up the volume on the quantum whispers of the early universe. This process can create a sharp peak in the power spectrum of density perturbations at a specific scale. Rather than a smooth distribution of fluctuation sizes, you get a burst of extremely large fluctuations concentrated within a narrow band of masses. And as we've discussed, where you have an overdensity that exceeds a critical threshold, you get gravitational collapse. In this scenario, that collapse would produce not a wide range of black hole masses, but a focused population of primordial black holes with very similar masses, all born from that single explosive moment during inflation. This is where specific models come into play. Take, for example, hybrid inflation. This model involves two fields interacting with each other, the primary inflaton field and a second waterfall field. The inflation proceeds normally until the inflaton reaches a critical value, which triggers a sudden instability in the waterfall field. This causes a very rapid second-order phase transition that ends inflation abruptly. This dramatic ending can create a significant spike in the power spectrum, potentially producing a large number of primordial black holes within a very specific mass range. The mass of those black holes is directly tied to the energy scale at which this transition happened, offering a clear prediction. Other models introduce deliberate features into the inflationary potential. A step or a dip in the potential can be engineered to create a similar amplifying effect. The presence of such a feature would cause the inflaton to slow down, enhancing the fluctuations at a corresponding scale. If the resulting primordial black holes were to be detected and their mass distribution carefully measured, it would be like reading the blueprint of that inflationary potential. We could pinpoint exactly where that feature was and what its shape must have been. This turns the abstract mathematics of inflation into something observable and tangible. Therefore, the search for primordial black holes is about much more than just finding dark matter or explaining solar system anomalies. It is a direct test of high-energy physics and our theories of the universe's birth. A confirmed detection of a significant population of these objects with a narrow mass range would be a stunning validation for the entire class of inflation models that predict such a spike. Conversely, if continued searches rule out primordial black holes across many orders of magnitude, it would severely constrain the types of inflationary potentials that are allowed, effectively ruling out many popular multi-field models and pushing us toward simpler, smoother versions of inflation. In this way, these elusive gravitational ghosts could become our most powerful guides to understanding the very first moment of everything. The detection of gravitational waves has opened an entirely new window onto the cosmos, allowing us to feel the very fabric of spacetime ripple with events of unimaginable power. Most of the mergers observed by the LIGO and Virgo observatories fit neatly into the expected narrative. They are the death spirals of black holes and neutron stars forged in the supernova explosions of massive stars. But a handful of these events have presented puzzles that challenge this straightforward story, and that's where the possibility of a primordial origin adds a thrilling layer of intrigue. When two black holes orbit each other, losing energy through the emission of gravitational waves, their inevitable merger sends a specific signal across the universe. The characteristics of that signal, the masses of the objects, their spins, and the orientation of their orbits tell a story about where they came from. Black holes born from dying stars typically exist within a certain mass range. A star must be massive enough to collapse, but there are also upper limits. Pair instability supernova, for instance, are thought to completely tear apart stars between approximately 130 and 250 solar masses, leaving no black hole behind. This creates a predicted gap or mass desert in the population of black holes. This is where the first compelling anomaly appears. The LIGO-Virgo collaboration has detected black holes merging with masses that seem to push against or even fall within this forbidden gap. The event known as GW1 90521, for example, involved two black holes of about 85 and 66 solar masses. The remnant was a black hole of 142 solar masses, placing it squarely in what was thought to be the pair instability mass gap. If these objects were formed from stars, their existence is deeply problematic for our models of stellar evolution. But if they are primordial, their formation faces no such restrictions. A primordial black hole could form with any mass, limited only by the size of the density fluctuation in the early universe. A black hole of 60, 80, or even 100 solar masses is perfectly plausible, offering a clean and elegant solution to this astrophysical puzzle. The spin of the merging black holes provides another crucial distinguishing clue. Black holes in a binary system that evolved from two massive stars are expected to have spins that are largely aligned with their orbital angular momentum. This is because they were born from a shared cloud of gas and have been orbiting each other for their entire existence, their spins influenced by their mutual dance. The data from several mergers, however, show hints of what are called precessing spins, spins that are tilted or even completely misaligned with their orbit. This suggests a much more chaotic history. A primordial black hole binary would have a very different origin story. Instead of being born together from a single stellar nursery, two primordial black holes would be wandering nomads drifting through the galaxy for billions of years. If two of them happen to pass close enough to each other, their mutual gravity could capture them into a binary orbit. This dynamical capture is a random, chaotic process far removed from the orderly collapse of a stellar nebula. It would naturally produce binaries with randomly oriented spins, perfectly matching the precession signals we are starting to see in the data. Furthermore, these ancient objects would have had billions of years to find each other and merge, meaning we could be witnessing the long-awaited conclusion of a gravitational dance that began in the universe's infancy. Perhaps the most statistically powerful signature would be the overall distribution of black hole masses. The stellar formation channel should produce a relatively smooth and predictable mass spectrum. In contrast, a population of primordial black holes would reflect the specific physics of their creation during inflation or phase transitions. If they were formed from a sharp spike in the inflationary power spectrum, as we discussed earlier, we might expect to see a pronounced peak in the merger rate at one very specific mass. Alternatively, a broader distribution could point to a different formation mechanism. As LIGO, Virgo, and future observatories like the Einstein Telescope and Cosmic Explorer detect thousands more events, they will be building a detailed census of the black hole population. If a significant fraction of these mergers cluster in ways that cannot be explained by stellar evolution, it will be some of the strongest indirect evidence yet that we are not just hearing from dead stars, but from the echoing whispers of the Big Bang itself. But the profound influence of these objects might extend even further, reaching back to solve one of the most fundamental mysteries of existence. Why is there anything at all? We live in a universe made almost entirely of matter. Every star, planet, and person is constructed from it. Yet our best theories of the Big Bang suggest that matter and antimatter should have been created in perfect, equal amounts. If that had happened, they would have immediately annihilated each other upon contact, leaving behind nothing but a dull sea of radiation. The fact that we are here means that for every billion antimatter particles created in the beginning, there must have been 1,000,000,001 matter particles. That tiny 1 part in a billion imbalance is all that saved the universe from total self-destruction. The process that created this slight favoritism for matter is called baryogenesis, and its precise mechanism remains one of physics' greatest unsolved problems. Intriguingly, primordial black holes could have been the unlikely architects of this cosmic asymmetry. One compelling theory suggests that the secret lies in the unique properties of Hawking radiation. Stephen Hawking's famous calculation showed that a black hole radiates particles as if it were a hot blackbody, but this radiation isn't necessarily a perfectly neutral soup of particles and antiparticles. The specific content of what radiates away depends on the quantum fields present and the mass of the black hole itself. For certain theoretical extensions of the standard model of particle physics, it's proposed that this radiation could actually violate what's known as CP symmetry. This is a fundamental principle that, roughly speaking, states the laws of physics should treat particles and antiparticles identically. If Hawking radiation from a primordial black hole somehow favored the emission of, say, electrons over positrons or quarks over antiquarks, then these evaporating black holes would have effectively injected an excess of matter into the early universe. Imagine trillions of these tiny, hot black holes peppering the cosmos in its first second. As they blaze away through Hawking evaporation, each one acts like a miniature factory, pumping out more matter than antimatter. While each individual black hole contributes only a minuscule excess, their collective output across the entire universe could have been enough to generate the entire observed matter-antimatter asymmetry we see today. The beauty of this idea is that it doesn't require any new physics to occur at extremely high energies everywhere in the universe. Instead, the extreme conditions are naturally provided by the black holes themselves, concentrating the energy and enabling processes that would be impossible in the wider, cooler cosmos. A second, equally fascinating mechanism involves the black holes not in their death throes, but in their vibrant youth through a process called gravitational baryogenesis. This concept hinges on a coupling between the expansion of the universe or the gravity of the black holes and the fields that distinguish matter from antimatter. In the incredibly dense environment around a newly formed primordial black hole, the gravitational field is immense. This intense curvature of spacetime could spontaneously break the symmetry between matter and antimatter, effectively creating a powerful energy barrier that treats particles and antiparticles differently. In this scenario, the gravitational influence of a massive population of primordial black holes would have fundamentally altered the playing field for all particle interactions happening in their vicinity. Certain particle decays or reactions that would normally produce equal amounts of matter and antimatter might, in the overwhelming gravitational pull of a black hole, tip the scales slightly in one direction. Over time, as these reactions occurred billions of times in the accretion disks or the surrounding space of countless black holes, a net surplus of matter could have gradually accumulated. The black holes act as gravitational catalysts, their immense presence biasing the entire universe toward the creation of the stuff we're made of. What makes both of these theories so powerful is their testability. They make specific predictions about the types and energies of particles that would be left over from these processes. If primordial black holes were responsible for baryogenesis, they might have left a faint but distinct imprint on the abundance of certain light elements forged in Big Bang nucleosynthesis, or perhaps produced a specific background of gravitational waves or high-energy neutrinos that our next-generation telescopes could hope to detect. Finding such a signal would do more than just explain why we exist. It would profoundly link our very presence to the most exotic and ancient objects in the cosmos, suggesting that the ultimate answer to the question of why there's something rather than nothing lies hidden within the depths of these gravitational ghosts. Moving from the grand question of cosmic existence to a more specific and brilliant mystery, we encounter one of astronomy's most perplexing signals: fast radio bursts. These are incredibly intense flashes of radio waves that last for just a few milliseconds, yet in that blink of an eye, they can release more energy than our sun does in weeks or even months. They arrive from deep space, often from other galaxies, and for years their origin was a complete enigma. While some have been traced to highly magnetic neutron stars called magnetars, a significant number remain unexplained, their source shrouded in mystery. This is where our ancient celestial nomads, primordial black holes, offer yet another startling possibility, suggesting that these brilliant cosmic flashes could be the result of a violent and fleeting encounter. One of the most compelling theories posits a direct and catastrophic collision. Imagine a primordial black hole, perhaps with the mass of a large asteroid but compressed into a space smaller than an atom, on a random journey through a distant galaxy. Its path is dictated by gravity alone, and on a cosmic timescale, a close encounter is almost inevitable. If this tiny, incredibly dense object were to plow directly into a neutron star, the result would be extraordinary. A neutron star is the ultra-compressed core of a dead star, so dense that a single sugar cube-sized amount of its material would weigh more than 1 billion tons. The impact of a primordial black hole would be unlike any ordinary asteroid strike. Upon hitting the neutron star's incredibly rigid surface, the black hole would not bounce or explode on the surface. Instead, its immense density would allow it to punch straight through the outer crust and plunge directly into the star's interior. As it travels through the hyper-dense matter of the neutron star, it would experience intense friction and gravitational interactions, transferring a tremendous amount of energy into the surrounding material almost instantaneously. This sudden, violent deposition of energy would create a powerful shock wave that ripples through the neutron star's magnetic field. It is this rapid disturbance of the magnetic field, a process known as magnetic reconnection, that could generate an intensely focused beam of radio waves shooting out from the star's magnetic poles. From our perspective, billions of light years away, we would see this event as a single, incredibly bright and unresolved millisecond flash, a perfect match for the profile of a non-repeating fast radio burst. But a collision isn't the only way a primordial black hole could be the culprit. The other mechanism brings us back to Stephen Hawking's brilliant work and the explosive end of a black hole's life. As we discussed, a low-mass primordial black hole would be nearing the end of its evaporation timeline around the current age of the universe. In its final second, its temperature skyrockets, and it releases its remaining mass energy in a tremendous burst of particles and radiation. While this is often thought of as a flash of gamma rays, the physics of the event is far more complex and could easily extend into the radio spectrum. The final evaporation wouldn't happen in a perfect vacuum. The black hole would be surrounded by plasma and likely possess a strong magnetic field itself, inherited from the galactic environment or generated by the charged particles in its Hawking radiation. As the black hole emits its last and most energetic particles, this burst would plow into the surrounding interstellar medium. The interaction would create a rapidly expanding shock front, and within this shock, electrons would be accelerated to nearly the speed of light. When these ultra-relativistic electrons spiral along magnetic field lines, they emit synchrotron radiation, a broad-spectrum glow that can be particularly bright at radio wavelengths. The entire event, the initial particle burst and the subsequent shockwave, would be extraordinarily brief, lasting only milliseconds, yet it would produce a brilliant, broadband radio flash that could travel across the universe to be detected by our telescopes. What makes both of these theories so powerful is that they make specific, testable predictions about the bursts we should observe. A collision with a neutron star would likely happen only once for that particular system, resulting in a burst that never repeats. The evaporation signal would also be a one-time event, the final death cry of a cosmic entity. This neatly explains the population of non-repeating fast radio bursts that have puzzled astronomers. Furthermore, the specific frequency structure of the burst, how its different radio frequencies smear out as they travel through intergalactic space, could carry an imprint of the event's extreme environment, potentially allowing us to distinguish it from a magnetar flare or other sources. As our radio telescopes like the CHIME array discover thousands more of these events, statistical analysis of their properties, their locations, and their energetics could finally reveal if a fraction of them are indeed the long-awaited signatures of these ancient gravitational ghosts meeting their dramatic end. To venture deeper into the exotic mechanisms that could have forged these ancient objects, we must introduce one of the most fascinating predictions of theoretical physics, cosmic strings. Picture the universe in its first moments cooling from an indescribably hot and unified state. As it expanded and cooled, the fundamental forces we know today, gravity, electromagnetism, and the nuclear forces, began to differentiate, freezing out from a single superforce in a series of spontaneous symmetry breaks. Much like cracks forming in ice as water freezes, these phase transitions could have created bizarre topological defects in the fabric of spacetime itself. Cosmic strings are one such defect. Unlike strings on a violin, these aren't made of any material substance. A cosmic string is a flaw in the geometry of the universe, an infinitely long, one-dimensional crack in spacetime so dense that just a single inch of it might contain more mass than a mountain range. They are theoretical entities, but if they exist, they would be under immense tension, capable of vibrating and oscillating at nearly the speed of light. Their gravitational influence would be profound, warping the space around them and acting as ultra-dense seeds around which matter could rapidly clump. The connection to primordial black holes emerges from the dynamic life cycle of these strings. A network of cosmic strings left over from the early universe would be a chaotic tangle of infinite lines and loops. As these loops oscillate, they lose energy by radiating gravitational waves, causing them to slowly shrink. But there's a critical point. If a loop is large enough and its oscillations are just right, it's possible that its self-gravity could become so overpowering that the entire loop collapses directly into a black hole. This isn't a collapse of matter, but a collapse of spacetime itself. This formation channel offers a compelling alternative to the standard density fluctuation model because it naturally produces a very specific and distinctive mass distribution for the resulting black holes. The mass of a black hole formed from a cosmic string loop is directly proportional to the length of the loop at the moment of its collapse. Since the string has a fixed density, a longer loop means more mass. The cosmic string network would have produced loops across a vast spectrum of sizes, but the physics governing their distribution might lead to a pronounced peak or a series of peaks in the mass spectrum of the resulting black holes. We wouldn't expect a smooth distribution, but rather a signature spike at a specific mass that corresponds to the predominant scale of the string network at the time of black hole formation. Therefore, the search for primordial black holes becomes a dual hunt. Finding a population of them isn't just evidence for the black holes themselves. It could also serve as the first indirect proof for the existence of cosmic strings. If astronomers were to detect a large number of primordial black holes that all seem to cluster around a very specific mass, say, all roughly 10,000 solar masses, it would be a powerful hint that they were all forged from cosmic string loops of a particular size. This would provide a stunning observational window into the physics of the universe's early phase transitions, offering clues about the energy scales at which these symmetries were broken. The implications stretch even further. The specific properties of these black holes, such as their expected spin, could also carry a trademark of their origin. A black hole born from the collapse of a cosmic string loop might have a very different spin parameter than one formed from a stellar collapse or a density fluctuation. As gravitational wave observatories like LIGO and Virgo become more sensitive and begin to measure the spins of merging black holes with greater precision, they could potentially identify outliers with spin distributions that point toward this exotic cosmic string origin. In this way, the detection of a specific class of primordial black hole could unravel multiple cosmic mysteries at once, confirming the existence of one of physics' most elusive hypothetical objects and revealing the forces that shaped the universe in its very first moments. For years, the hunt for dark matter took a fascinating detour into our own galactic backyard, focusing on a class of objects known as massive astrophysical compact halo objects. The idea was straightforward and compelling. Perhaps the dark matter halos surrounding galaxies weren't made of exotic particles, but of ordinary, familiar stuff that just doesn't shine. Think of faint, failed stars called brown dwarfs, lonely planets wandering between stars, or ancient, cold white dwarfs and neutron stars. These objects would have mass and exert gravity, but they'd be virtually invisible to our telescopes, making them perfect candidates to explain the missing mass. The primary tool for this search was gravitational microlensing, a beautiful application of Einstein's theory of relativity. The concept is simple yet powerful. If a massive, compact object like a macho drifts through the halo of our galaxy and passes almost perfectly between Earth and a distant star in a neighboring galaxy like the Large Magellanic Cloud, its gravity will act as a natural lens. For a brief period, ranging from hours to months, the background star will appear to temporarily brighten as the gravitational field of the macho focuses its light toward us. By meticulously monitoring millions of stars for these characteristic flashes, astronomers could statistically determine how many such dark objects were lurking in the galactic halo. The initial results from pioneering surveys in the 1990s, like the Macho project and the French Eros survey, sent waves of excitement through the astrophysics community. They detected a handful of these microlensing events, more than what would be expected from known stellar populations, but significantly fewer than what would be required if Macho made up 100% of the dark matter. The data suggested that these objects could potentially account for up to 20% of the Milky Way's dark halo. It was a tantalizing hint that some of the dark matter might indeed be hiding in these compact, macroscopic objects. But here's where the story takes a turn, and where primordial black holes re-enter the narrative with a compelling alternative explanation. The constraints from these early surveys were powerful, but they were primarily sensitive to Macho in a specific mass range, roughly from a millionth of a solar mass to about 10 solar masses. This is the mass range of planets, brown dwarfs, and stellar remnants. The data effectively ruled out the possibility that such objects could be the dominant form of dark matter. However, the microlensing signature of a primordial black hole is identical to that of a brown dwarf or a rogue planet of the same mass. Gravity doesn't discriminate based on composition. So, the same events that suggested a population of Macho could also have been caused by a population of asteroid mass or stellar mass primordial black holes. This is where more modern and sensitive surveys like the optical gravitational lensing experiment, or OGLE, come into play. OGLE has been a workhorse of time-domain astronomy for decades, monitoring hundreds of millions of stars in the Magellanic Clouds and the galactic bulge with unprecedented precision. Its vast dataset has placed incredibly tight constraints on the abundance of compact objects within the critical mass window. OGLE results have largely confirmed and refined the earlier work, showing that objects between roughly 10 to the power of -8 solar masses and 10 solar masses can constitute only a tiny fraction of the galactic dark matter halo, perhaps less than 1%. But these constraints have also helped to sculpt the remaining windows of possibility for primordial black holes. While OGLE data closed the door on planet-sized and stellar-sized objects as the primary dark matter component, it left two windows intriguingly ajar. The first is for much smaller black holes in the asteroid mass range. These would be so light that their microlensing events would be impossibly brief for current surveys to detect. The brightening of the background star might last only a few seconds or minutes. The second window is for much heavier black holes above about 50 solar masses. These would be so massive that their lensing events would be exceedingly rare and very long, stretching over years, making them difficult to distinguish from other variable stars. Therefore, the legacy of the Macho searches is not a closed case but a refined map. They didn't find a population of dark matter planets or dead stars, but they brilliantly charted the territory, telling us where we cannot look. The few events that were detected remain intriguing anomalies. Could some of them have actually been primordial black holes? It's a distinct possibility. Their existence in the still allowed mass ranges would perfectly align with the microlensing data, offering an elegant solution that requires no new types of ordinary matter. Instead of faint stars or planets, the lensing objects could be the ancient dark remnants of the Big Bang itself, their gravitational influence the only sign of their passage through the eternal night of the galactic halo. Now, this journey into the deepest layers of cosmic structure leads us to one of the most mind-bending and speculative theories of all: the possibility that these ancient black holes are not endpoints but gateways. To venture down this path, we need to revisit one of the most iconic solutions to Einstein's equations of general relativity, the Einstein-Rosen bridge, more popularly known as a wormhole. The mathematics shows that the interior of a black hole solution can be extended to form a tunnel or bridge, connecting it to another region of spacetime. For a classic black hole formed from a star, this bridge is thought to be unstable, pinching off into a singularity before anything could ever traverse it. It's a tantalizing mathematical possibility that seems physically impossible, but the conditions of the very early universe might have rewritten those rules entirely, thanks to the strange and dominant influence of quantum mechanics. In that first seething fraction of a second, the extreme density and temperature could have allowed for quantum gravitational effects to stabilize these bridges, at least temporarily. Under these conditions, the tunnel might not have led to a deadly singularity, but to its theoretical opposite, a white hole. While a black hole is a region from which nothing can escape, a white hole is a region into which nothing can enter, a source of matter and energy that only pours outward. It's like a black hole playing the cosmic film in reverse. If a primordial black hole formed in that first instant, its incredible density might have been sufficient for these quantum gravitational forces to take hold, effectively propping open the throat of the wormhole and connecting it to a white hole erupting into another part of the universe, or even into a completely different universe altogether. In this breathtaking scenario, a primordial black hole wouldn't be a cosmic dead end. It would be a one-way passage, a natural transporter forged in the fire of the Big Bang. Matter falling into it in our universe could, in principle, be expelled from its white hole counterpart somewhere else. The implications of this are staggering to contemplate. First, it offers a potential mechanism for the universe to achieve a kind of equilibrium. If regions became too overdense, they could collapse into black holes and have their contents redistributed elsewhere through these tunnels, preventing runaway collapse and smoothing out the cosmos. Second, and far more speculatively, it provides a possible origin for the universe itself. Some cosmologists, like Carlo Rovelli, have explored the idea that the Big Bang could be seen as the white hole end of a tunnel from a previous universe. In this view of cyclic cosmology, our entire expanding universe might be the result of a massive white hole eruption, with primordial black holes acting as the tiny quantum gravitational sewers, eventually draining our universe to feed the next one in an endless cycle of cosmic rebirth. Of course, this remains one of the most speculative ideas in theoretical physics, as there is no known mechanism to create a stable, traversable wormhole and no observational evidence for white holes. But it demonstrates the profound power of primordial black holes as theoretical tools. They push us to the very edge of known physics, forcing us to ask questions about the fundamental nature of spacetime, causality, and the ultimate origin of everything we see. Whether they are dark matter, galactic seeds, or cosmic gateways, their potential existence challenges us to think bigger and deeper about the universe and our place within it. This brings us to one of the most perplexing and fundamental puzzles in theoretical physics, the black hole information paradox. At its heart, this isn't just a technical problem about stellar remnants. It strikes at the very core of our understanding of reality, questioning whether the universe is ultimately predictable and trustworthy. The paradox emerges from a direct conflict between two pillars of modern physics, Einstein's general relativity and quantum mechanics. According to general relativity, a black hole is defined solely by its mass, electric charge, and spin. Everything else about the matter that formed it, the type of atoms, their arrangement, whether it was made from a star or a library of books, is seemingly erased forever when it crosses the event horizon. This presents no problem for classical physics. However, quantum mechanics has a fundamental rule called unitarity. It states that information, the complete quantum state of a system, can never be truly lost or destroyed. It can be scrambled, spread out, and become incredibly difficult to read, like shredding a document and throwing the confetti into a hurricane. But in principle, the information must always be preserved. If you could somehow reverse time and gather every single piece, you could reconstruct the original document. The black hole information paradox asks a devastatingly simple question. When a black hole evaporates completely via Hawking radiation, what happens to all the information about the stuff that fell in? If it's truly gone, quantum mechanics is wrong. If it's not, general relativity, which says the information is irretrievably trapped inside, must be incomplete. Primordial black holes, especially the very light ones nearing the end of their evaporation, are not just potential subjects in this debate. They could be the ideal natural laboratories for resolving it. Their entire life cycle, from birth in the Big Bang to their final explosive second, plays out the entire information drama on a compressed timescale. How information might escape a dying black hole is a central question, and two leading ideas hinge on the nature of Hawking radiation itself. The first possibility is that the information is subtly encoded in the radiation itself. Although Hawking's original calculation suggested the radiation was purely thermal, carrying no information other than the black hole's temperature, this might not be the full story. Later work suggests that quantum correlations between particles emitted at different times could actually imprint the information of what fell into the black hole onto the outgoing radiation. It would be an incredibly complex and subtle code, but in principle, a full record of every particle that ever crossed the event horizon would be contained in the precise pattern of the Hawking radiation emission over the black hole's entire lifetime. When the black hole finally vanishes, the information isn't lost. It's been returned to the universe, albeit in a form so scrambled we would likely never be able to decode it. For a primordial black hole, observing the exact spectrum and particle content of its final burst could reveal tiny deviations from a perfect thermal signature, the telltale fingerprints of information being carried away. The second major proposal is even more radical, the final state conjecture. This idea suggests that the laws of quantum mechanics modify the very center of a black hole, replacing the classical singularity with a dynamic quantum bounce. In this scenario, the interior of the evaporating black hole doesn't simply end in a singularity. Instead, it undergoes a quantum phase transition, transforming into a tiny, stable remnant no larger than the Planck length. This remnant would contain within its structure the entire quantum information of everything the black hole ever consumed. It wouldn't radiate further. It would just sit there as an infinitesimally small, incredibly dense fossil, a permanent archive of the black hole's history. The evaporation would appear complete to an outside observer, but the information would be preserved forever in this stable endpoint. The existence of such remnants would have profound implications. If primordial black holes are dark matter, these Planck-scale fossils could be the actual dark matter particles saturating the universe. Their detection would be nearly impossible due to their size, but their collective gravitational influence would be immense. Furthermore, the fact that they retain information resolves the paradox without violating quantum mechanics. Discovering a population of evaporating primordial black holes would allow us to test these theories directly. By analyzing the precise energy signature of their final burst with futuristic gamma-ray or gravitational wave observatories, we could search for the non-thermal correlations that signal information escape. Alternatively, if we find that black holes seem to vanish completely without any such signal, it would lend weight to the remnant idea. Either outcome would provide the first experimental data from nature on how to reconcile gravity and quantum mechanics, turning a philosophical debate into an observational science and finally answering whether the universe forgets anything at all. But our journey doesn't end within the confines of our own universe. One of the most profound and mind-expanding possibilities is that these ancient objects are not merely relics of our cosmic birth, but could be the first tangible evidence for something far grander, the multiverse. This idea pushes beyond the boundaries of known physics, suggesting that our universe might be just one bubble in a vast, frothing cosmic foam of countless other universes, each with its own unique laws and constants. If that's true, how could we ever hope to find evidence? The answer might lie in the gravitational scars left by collisions between these bubbling realms, scars that could take the form of primordial black holes. This incredible concept is deeply tied to the theory of eternal inflation. Picture the multiverse not as a static collection of universes, but as an endlessly bubbling cauldron of spacetime. The vacuum energy that drove our own universe's inflation continues to drive the expansion of a much larger background meta-universe. In this violent, high-energy environment, pockets of lower-energy vacuum can spontaneously form, like bubbles appearing in a pot of boiling water. Each of these bubbles represents a new universe nucleating and beginning its own expansion, rapidly cooling and settling into its own set of physical laws. Our entire observable cosmos could be just one such bubble. Now, imagine two of these expanding bubble universes born relatively close to each other in the inflationary background. As they grow, they will eventually collide. The boundary where they meet would be a region of unimaginable energy and density, a cosmic shockwave rippling through the very fabric of reality. According to models developed by physicists like Stephen Feeney, these collisions would not simply bounce off each other. The immense energy released at the impact boundary could be sufficient to trigger gravitational collapse, condensing a region of spacetime so dense that it forms a black hole. This wouldn't be a black hole formed from matter within a universe, but a black hole formed from the very structure of the collision between universes. It would be a primordial black hole with a truly exotic origin story, a fossilized bruise from a long-ago encounter with a separate reality. The properties of such a black hole would be a dead giveaway. Because it was forged in a collision of two distinct vacuum states, it might carry an imprint of that encounter. The resulting black hole could have a very specific mass distribution, one that is linked to the energy scale of the inflation field and the dynamics of the bubble collision. If astronomers were to discover a population of primordial black holes that all share a very narrow, specific mass, one that doesn't neatly align with predictions from standard inflationary models, it could be the signature we're looking for. It would be evidence that our universe once touched another, a permanent gravitational monument to an event that occurred in the wider multiverse. Another fascinating pathway connects to the idea of higher dimensions, a key component of string theory. This theory proposes that the fundamental particles we see are actually vibrations of tiny, multi-dimensional strings, and that our universe may have more than the three spatial dimensions we experience. These extra dimensions are thought to be curled up or compactified on an incredibly small scale. However, in the extreme energies of the very early universe, these dimensions might have played a much more active role. In some brain cosmology models, our universe is a three-dimensional membrane, or brane, floating within a higher dimensional bulk. Other branes, representing other universes, could be floating in this same bulk. If two such branes were to collide or interact, the transfer of energy could be immense. Such a collision could create localized points of incredible density right on our brain points that promptly collapse into black holes. Once again, the signature would be in the details. Black holes formed from brain collisions might have distinctive properties, such as unusual spin orientations or a specific gravitational wave signature when they merge, that would set them apart from black holes with a purely four-dimensional origin. The search for these multiverse signatures is not just a flight of fancy. It's a serious scientific endeavor that turns the hunt for primordial black holes into a test of our most ambitious cosmic theories. Finding them would do more than just identify a new class of astrophysical object. It would provide the first empirical evidence that our universe is part of a much larger and even more strange multiversal structure. It would mean that the primordial black holes dotting our galaxy are not just ancient, but are visitors from a frontier beyond space-time as we know it, offering us a fleeting glimpse into the infinite possibilities of existence. Within the mysterious realm of dark matter, one hypothetical particle has captured the imagination of physicists for decades: the action. Initially proposed to solve a complex problem in particle physics known as the strong CP problem, actions have since become a leading candidate for the universe's missing mass. These particles are theorized to be incredibly light, possibly billions of times lighter than an electron, and they would interact with ordinary matter only very weakly and through gravity. This makes them cold dark matter, moving slowly in the early universe and clumping together to form the gravitational scaffolding for galaxies. But the story becomes even more fascinating when we consider how these elusive particles might interact with another cosmic mystery: primordial black holes. Their relationship could be a symbiotic one, with each influencing the other's existence and creating unique observational signatures. One compelling theory suggests that the presence of actions could have actually enhanced the formation of primordial black holes in the universe's first moments. In the hot, dense plasma of the Big Bang, actions wouldn't have been individual particles yet. Instead, they would have existed as a coherent field oscillating throughout space. In some models, this field can collapse into dense, knot-like structures called action miniclusters. These miniclusters are gravitational hotspots, regions where the density of actions is significantly higher than the surrounding average. If a primordial density fluctuation happened to occur in a region already dominated by one of these action miniclusters, the combined density could easily surpass the critical threshold needed for gravitational collapse. The minicluster would act as a seed, providing a massive core around which a primordial black hole could form much more easily than in a region of ordinary radiation and matter alone. This partnership could have dramatically increased the number of black holes created, making them far more abundant than models without actions would predict. The interaction doesn't stop at formation. Once a primordial black hole exists, it can profoundly influence any surrounding actions, and this dance creates some of the most promising opportunities for detection. Due to their incredibly low mass, actions behave less like discrete particles and more like a wave on a cosmic ocean. Their quantum wavelength can be vast, even spanning astronomical distances for the lightest actions. When such a wave encounters the intense, curved spacetime around a black hole, something remarkable can happen. The action field can become gravitationally bound to the black hole, forming a vast, diffuse cloud that envelops it like a shroud. This isn't a cloud of gas, it's a coherent quantum wave oscillating at a very specific frequency dictated by the action's mass. This action cloud is stable for a time, but it is not permanent. Through a process known as superradiance, the black hole can actually transfer its own rotational energy into the cloud. Imagine the black hole spinning and the action cloud acting like a drag, sapping its angular momentum and causing it to slow down. As this happens, the cloud grows denser and more populated with actions. This process can continue until the black hole's spin is reduced below a critical threshold, at which point the superradiance shuts off. What remains is a massive, humming cloud of actions around a now slower spinning black hole. This setup is a gift to astronomers because this dense cloud is unstable in a very specific way. The actions, through their weak self-interactions, can annihilate and convert their mass directly into photons. This would produce a continuous, monochromatic beam of electromagnetic radiation, a very specific and steady frequency of light that is directly tied to the mass of the action. For a hypothetical action with a mass of a few microelectronvolts, this emission would appear in the radio band of the spectrum. We would therefore expect to see black holes of a certain mass emitting a powerful, persistent radio signal at a single, pure frequency, a clear beacon that cannot be easily explained by any other known astrophysical process. Searches are already underway for these mysterious signals. radio telescopes are scanning known black holes, both stellar mass and supermassive, looking for any sign of this unique narrow-band emission. The discovery of such a signal would be a monumental event, serving as a direct and simultaneous confirmation of two of physics' greatest mysteries: the existence of action dark matter and the presence of primordial black holes. It would reveal a hidden dialogue between the quantum world and the gravitational giants, showing that these ancient objects are not isolated monsters but active participants in the cosmos, still shaping and being shaped by the invisible sea of particles that fills the void. While black holes are often seen as disruptors, their influence might extend to the very building blocks of our universe, leaving a subtle imprint in the oldest fossils we can study, the primordial elements. To understand this, we need to journey back to a time when the entire cosmos was a nuclear fusion reactor. In the first 3 to 20 minutes after the Big Bang, the universe had cooled just enough for protons and neutrons to begin fusing into the first atomic nuclei, but it was still too hot and dense for these new nuclei to capture electrons and form stable atoms. This brief, explosive period is known as Big Bang nucleosynthesis, and it produced almost all the hydrogen and helium in the universe today, along with trace amounts of lithium and deuterium. The precise ratios of these elements are a powerful probe of the conditions in that infant cosmos, and any deviation from the predicted abundances points to new physics at play. This is where primordial black holes enter the story, not as destroyers but as potential polluters of this pristine nuclear soup. The constraining power of these elemental abundances is immense. For decades, the remarkable agreement between the predicted and observed amounts of helium-4, deuterium, and lithium-7 has been a cornerstone of the Big Bang model. But this agreement also sets very strict limits on anything that could have disturbed this delicate process. If too many primordial black holes existed during nucleosynthesis, they would have inevitably altered these ratios, and we can calculate exactly how. Their impact could have been felt through two distinct channels: direct injection of matter and subtle manipulations of the universe's expansion rate. The first and most dramatic effect comes from Hawking radiation. A light primordial black hole with a mass around 1 billion metric tons would have been incredibly hot and active during the nucleosynthesis era. As it evaporated, it wouldn't just be emitting photons, it would be a prolific factory for all kinds of fundamental particles, including quarks and gluons. These particles would hadronize, meaning they would quickly combine to form protons, neutrons, and pions. This process is known as hadron injection. Imagine trillions of these tiny black holes peppered throughout the universe, each constantly spitting out fresh batches of protons and neutrons into the surrounding plasma. This would be like adding new ingredients to a carefully measured recipe while it's still cooking. This injection of new nucleons would have several cascading effects. First, it would increase the overall density of baryons, the class of particles that includes protons and neutrons. The standard Big Bang nucleosynthesis model works with a fixed baryon-to-photon ratio, and adding extra baryons from black hole evaporation would throw this carefully balanced parameter off. More neutrons in particular would mean more fuel for helium-4 production, potentially leading to an overabundance that contradicts what we observe. Furthermore, the injected high-energy hadrons could have initiated spallation reactions, smashing into existing light nuclei and breaking them apart. For instance, a high-energy proton could collide with a helium-4 nucleus and fragment it into deuterium and tritium. This could simultaneously deplete the amount of helium and boost the abundance of deuterium, again creating a mismatch with the observed values that our models struggle to explain. The second influence is more subtle but equally significant: gravitational effects on the expansion rate. The success of Big Bang nucleosynthesis hinges on a very specific timeline. The universe had to expand and cool at a precise rate to allow the nuclear reactions to proceed correctly, and then freeze out at the right moment. If the expansion had been too fast, neutrons would have decayed away before they could be incorporated into helium, leading to a helium shortage. If it was too slow, nearly all the deuterium would have been fused into helium, leaving almost none behind. The presence of a significant population of primordial black holes would have contributed to the total energy density of the universe. Even if they weren't evaporating, their sheer mass would have gravitationally pulled on the fabric of spacetime, subtly altering the rate of the universe's expansion during those critical first few minutes. This means the elemental abundances we measure today act as a cosmic historian, recording the conditions during the universe's first moments. By comparing the observed ratios of light elements to the precise predictions of nucleosynthesis models, cosmologists can work backwards. They can ask how many primordial black holes of a given mass could have been present without messing up the numbers we see. The answer is that the constraints are incredibly tight. For black holes with masses that would have been evaporating during nucleosynthesis, the limits are severe. The hadron injection from their evaporation would have been so disruptive that they could have constituted only a minuscule fraction of the universe's density at that time. For heavier, more stable black holes, the constraints are based on their gravitational influence, and they too are limited to being only a very small component of the cosmic budget during that epoch. This doesn't rule out primordial black holes entirely, but it precisely sculpts the allowed parameters for their existence. It tells us that if a large population of them formed, they must have either been very light and evaporated completely before nucleosynthesis began, or they must have been very heavy and thus too sparse to significantly affect the expansion rate or the nuclear processes. This elegant use of primordial element abundances is a perfect example of cosmic detective work, using the oldest evidence we can find to constrain some of the most exotic objects we can imagine, ensuring our theories of the very early universe remain consistent with the tangible chemistry of the cosmos we observe today. While we often look to the far reaches of space for answers, some of the most compelling evidence for these ancient objects might be etched into the oldest light we can see, the cosmic microwave background. This faint glow saturating the entire sky is the cooled remnant of the universe's fiery birth, a snapshot taken when the cosmos was just 380,000 years old. It is our most powerful window into the early universe, and its subtle variations in temperature hold secrets about the conditions that prevailed long before the first stars flickered to life. If primordial black holes were indeed present in that nascent era, their profound gravitational influence and energetic activity would have left permanent scars on this cosmic photograph, providing us with a way to detect their ghostly presence billions of years later. The primary method for this search involves looking for the energetic fingerprints of evaporating black holes. Imagine the universe during its first few 100,000 years, a hot, opaque plasma of ions and electrons constantly scattering light. As it expanded and cooled, electrons and protons finally combined to form neutral hydrogen atoms in an event called recombination. This suddenly made the universe transparent, allowing photons to travel freely, and that first burst of free-flying light is what we detect today as the CMB. The precise process of recombination and the way energy was distributed throughout the plasma is exquisitely sensitive to any outside interference. If a significant population of light primordial black holes was evaporating during this critical period, they would have acted as countless tiny engines, pumping high-energy radiation and particles into the primordial soup. This injection of energy would have had two major effects. First, it would have slightly delayed the process of recombination itself. The extra energy from Hawking radiation would have kept the plasma ionized for a fraction longer than it otherwise would have been, altering the precise timeline of when the universe became transparent. Second, and more importantly, this energy injection would have modified the way energy was distributed among the particles, effectively transferring energy from the black hole's radiation into the electron gas. This would have heated the electrons to a temperature slightly different from that of the cosmic background photons themselves. Both of these effects, the delayed recombination and the modified way energy was shared between matter and radiation, would have left a distinct imprint on the statistical properties of the CMB's temperature and polarization patterns. Sophisticated analysis of data from the Planck satellite has already placed incredibly tight constraints on this possibility. By comparing the observed CMB fluctuations to detailed theoretical models that include such energy injection, cosmologists have been able to rule out the scenario where a large population of evaporating primordial black holes contributed significantly to the universe's energy budget during the recombination era. This doesn't mean they didn't exist, but it tells us they couldn't have been numerous enough to disrupt the beautifully calibrated physics of the early universe that we observe encoded in the microwave background. This effectively closes the door on light, evaporating black holes as a dominant component of the universe at that time, reinforcing the idea that if they are out there, they must either be very light and have evaporated much earlier or be much heavier and more stable. However, there is a second, more subtle way these gravitational ghosts could have marked the CMB through their sheer gravity. The immense mass of a primordial black hole warps the fabric of spacetime around it, bending the path of any light that passes nearby. This is gravitational lensing. The light from the CMB has been traveling for over 13 billion years to reach us, and on its long journey, it may have passed close to any number of massive, compact objects. If a primordial black hole drifted between us and the surface of last scattering, its gravity would have subtly distorted the CMB light rays, creating a unique signature. This lensing effect would manifest in two ways. For a single, very massive black hole, it could create a specific circular distortion in the CMB temperature map, a kind of cold or hot spot with a distinctive pattern. While searches for these individual imprints have so far come up empty, they continue to be a target for analysis. The more promising and statistically powerful method involves the collective lensing effect of a whole population of black holes. If they were abundant enough, their combined gravitational influence would have gently sheared the CMB light all across the sky, adding a specific statistical pattern to the observed temperature fluctuations. This pattern is what cosmologists call a non-Gaussian signature. It's a telltale sign that the simple, random fluctuations from inflation have been subtly processed and twisted by the gravitational influence of intervening objects. The hunt for this signal is incredibly challenging, as it requires separating it from the lensing effect caused by all the other matter in the universe, the collective gravity of galaxies and galaxy clusters. Yet, as our measurements of the CMB become ever more precise, particularly with future observatories, the sensitivity to these subtle effects will increase dramatically. Finding a lensing signature that is inconsistent with the expected distribution of ordinary matter would be a powerful hint that a hidden population of massive, compact objects, primordial black holes, is out there, their presence revealed only by the way they have bent the oldest light in the universe on its journey to our telescopes. For decades, the leading theoretical framework for explaining dark matter has revolved around the idea of entirely new, undiscovered particles, with supersymmetry standing as the most celebrated candidate. Supersymmetry, or SUSY, proposes that every known particle has a heavier superpartner, and the lightest of these superpartners could be stable, electrically neutral, and pervasive, perfectly fitting the description of dark matter. This elegant idea promised not only to solve the dark matter puzzle, but also to resolve other deep issues in particle physics. However, after years of meticulous searching with powerful particle colliders like the Large Hadron Collider and sensitive underground detectors, no evidence for these superpartners has been found. This persistent lack of discovery has forced physicists to re-examine the foundations of the problem and ask a more fundamental question: what if dark matter isn't a particle at all? This is where primordial black holes re-enter the stage with a compelling and radically different proposition. They offer a solution that requires no new physics beyond our well-tested understanding of Einstein's gravity and the standard Big Bang model. The concept is beautifully simple. The invisible mass holding galaxies together could be made of compact, astronomical objects that formed in the universe's first instant, rather than a sea of exotic particles. This idea isn't new. It was first seriously considered by Stephen Hawking and others in the 1970s, but it was largely set aside as the particle physics approach, with its promise of unifying fundamental forces, gained dominance. The continued failure to detect those particles has now sparked a major resurgence of interest in this gravitational alternative. The theoretical motivation for this shift is powerful. Primordial black holes are a natural prediction of many well-motivated models of the early universe, particularly those involving periods of enhanced density fluctuations during cosmic inflation. Their existence doesn't require inventing new quantum fields or particles. It simply requires that the chaotic conditions of the Big Bang were violent enough to knot spacetime itself into these gravitational pits. Furthermore, they are inherently dark. By their very definition, they do not emit light, and their only interaction with ordinary matter is through the familiar, predictable force of gravity. This perfectly matches the observed behavior of dark matter, which shapes the cosmos through gravity while remaining otherwise invisible and seemingly non-interacting. However, a viable theory must withstand rigorous experimental scrutiny, and the journey to constrain possible black hole dark matter has been a masterclass in astronomical detective work. Researchers have used a vast array of observational techniques to rule out wide swaths of potential mass ranges. The most powerful constraints come from gravitational microlensing surveys. The principle is straightforward. If a massive compact object passes in front of a distant star, its gravity will bend and focus the star's light, causing a temporary brightening. By monitoring millions of stars for years, projects like OGLE and the Subaru Hyper Subprime CAM have determined that black holes in the mass range of large asteroids to about 10 times the mass of Jupiter cannot make up all of the dark matter. There simply aren't enough of these lensing events occurring. Other methods provide complementary constraints. The precise measurements of the cosmic microwave background by the Planck satellite are exquisitely sensitive to any energy injection in the early universe. If too many black holes were accreting matter or evaporating during the first few 100,000 years, they would have left a clear and disruptive imprint on the CMB's temperature patterns, an imprint that is not observed. This effectively rules out very light, evaporating black holes and very heavy ones above several hundred solar masses as the primary dark matter constituent. The distribution of stars in nearby dwarf galaxies also argues against a large population of black holes in certain mass ranges, as their gravitational tug would disrupt these fragile stellar systems in ways we do not see. Yet, despite this extensive search, two tantalizing mass windows remain intriguingly open. The first is the so-called asteroid mass window for black holes weighing between 1 billion and 1 trillion metric tons. These would be smaller than a proton yet possess the mass of a mountain. Their microlensing events would be impossibly brief for current surveys to detect, and they would have evaporated too early to affect the CMB. The second window is for stellar mass black holes between roughly 1 and 100 solar masses. This is particularly fascinating because it directly overlaps with the masses of the black holes detected by LIGO and Virgo through gravitational waves. The discovery of these merging black holes, some of which were surprisingly heavy, immediately revived the debate, suggesting that a primordial origin for at least a fraction of them is still very much on the table. This presents a fascinating possibility. Dark matter may not be a single, monolithic substance. The universe's missing mass could be a mix, with primordial black holes in these allowed mass ranges accounting for a significant portion, while another component, perhaps a lighter particle like the action, makes up the rest. This hybrid model offers a way to satisfy all the existing constraints while still leveraging the gravitational power of these ancient objects. The ongoing search, therefore, is not just a binary yes or no endeavor, but a detailed campaign to measure the exact population and mass spectrum of any primordial black holes out there, determining what fraction of the dark matter budget they might finally balance. But the significance of these ancient objects might extend far beyond the confines of cosmology and into the very laws of physics themselves, offering a potential key to unlocking one of the most profound questions in all of science. Are the fundamental constants of nature truly constant? For centuries, we've operated under the assumption that the numbers which dictate how the universe works, the speed of light, the strength of gravity, the mass of an electron, are fixed and unchanging, the same everywhere and for all time. But what if that's not the case? Some of the most cutting-edge theories, particularly those attempting to unify gravity with the other forces, suggest that these constants could have been different in the incredibly high-energy environment of the early universe and may even be slowly evolving even now. Proving this, however, has been a monumental challenge as it requires comparing precise measurements across billions of years. This is where the humble, evaporating primordial black hole could become one of the most powerful time-keeping devices ever imagined. The secret lies in the unique and predictable nature of Hawking radiation. As we've discussed, a black hole evaporates by emitting a spectrum of particles, and the precise energy of that radiation is dictated by the black hole's temperature, which is itself determined by a simple formula involving fundamental constants. Most critically, the rate at which a black hole loses mass depends on the gravitational constant big G, and the values that govern the quantum world, like the fine structure constant which sets the strength of electromagnetic interactions. If any of these constants were different in the past, it would have directly altered how quickly primordial black holes evaporated. A smaller value for the gravitational constant in the early universe, for instance, would have made gravity weaker, meaning black holes would have evaporated more slowly. A change in the fine structure constant would have modified how efficiently different types of particles were radiated away. The entire life history of a primordial black hole is, in effect, a frozen record of the physics that prevailed during its lifetime. This turns a population of these objects into a distributed network of cosmic clocks, each ticking at a rate set by the fundamental laws of its era. By studying the remnants of this population today, we could look for a telltale signature of inconstancy. Imagine if we could somehow measure the mass distribution of primordial black holes across the universe. If the fundamental constants have always been the same, we would expect a relatively smooth distribution that aligns with a specific model of their formation, like a spike from a particular inflation model. But if the constants were variable, it would create a distinct anomaly in that distribution. For example, if the gravitational constant was slightly stronger in the past, black holes that formed early on would have evaporated much faster than our current models predict. This would mean we'd see far fewer very light black holes today than we should, because they would have died off prematurely. The observed mass spectrum would have a specific dip or cutoff that points directly to a historical variation in a fundamental constant. The most exciting prospect involves not just their final mass, but the detailed spectrum of their final burst. When a low-mass primordial black hole nears the end of its life, its evaporation accelerates into a catastrophic runaway process, emitting a flash of high-energy particles. The exact energy of this flash, the specific wavelengths of gamma rays it produces, is exquisitely sensitive to the values of the fundamental constants at that very moment. Now consider that we might be able to observe the death throes of black holes at vastly different cosmological distances. A flash detected from a source a billion light-years away is an event that happened a billion years ago. A flash from 10 billion light-years away is a signal from the universe's youth. If we could collect a large sample of these evaporation events from different epochs and precisely measure their energy spectra, we would be collecting a direct data set on how the fundamental constants have behaved over cosmic time. A slight but systematic shift in the peak energy of these gamma-ray bursts across different redshifts would be the smoking gun, undeniable evidence that the rules of the game have been changing. This approach offers a clarity that other methods struggle to achieve. Techniques like studying the absorption lines in incredibly distant quasars are powerful, but they can be plagued by systematic uncertainties and complex astrophysical backgrounds. The spectrum of a black hole's final burst, by contrast, is a relatively clean theoretical prediction. It is a direct consequence of well-understood thermodynamics and quantum field theory in curved spacetime. While still incredibly challenging to observe, its interpretation would be far more straightforward. A confirmed variation would send shockwaves through the world of physics, forcing a radical rewrite of our understanding of the universe's fundamental architecture and providing crucial experimental data to guide the development of a final theory of everything. These cosmic ghosts, therefore, may be more than just relics. They could be the ultimate historians, carrying encoded within their life cycles a chronicle of the laws of physics themselves, waiting for us to learn how to read their story. Now, to venture into one of the most speculative and mind-bending territories, we must consider the possibility that the universe we perceive is not all there is. What if the reality we experience, with its 3 dimensions of space and 1 of time, is merely a slice of a far richer, higher-dimensional cosmos? This isn't just science fiction. It's a serious proposal from string theory and brain cosmology, suggesting that the fundamental building blocks of reality are tiny, vibrating strings existing in 10 or 11 dimensions. These extra dimensions are thought to be curled up or compactified on an incredibly small scale, which is why we don't notice them in everyday life. But in the extreme energies of the Big Bang, they would have been unfurled and dominant, and their existence could have dramatically altered the birth and life of primordial black holes, turning them into unique probes for these exotic theories. The connection hinges on gravity's unique role in these models. In many brain world scenarios, our entire universe is a 3-dimensional membrane or brain floating within a higher dimensional bulk. The particles we know and love, electrons, quarks, photons, are stuck to our brain like waves on the surface of an ocean. But gravity, which is the curvature of spacetime itself, is different. It can leak out into the extra dimensions. This could explain why gravity is so astonishingly weaker than the other fundamental forces. Its strength is simply diluted as it spreads out into these unseen spatial volumes. This leakage has a profound and testable consequence. At very small distances, or equivalently at very high energies, gravity would become much stronger than we expect. And there are few places where gravity is stronger than in the formation of a black hole. This changes the rules for how a primordial black hole could be born. In our standard 4-dimensional universe, a certain density is required to collapse a region into a black hole. But if extra dimensions exist and gravity is stronger at high energies, the threshold for black hole formation drops significantly. In the early universe, it would have been far easier to create black holes, regions of space that would have been too smooth to collapse in a 4-dimensional model could have readily formed black holes in a higher dimensional one. This means that theories with extra dimensions naturally predict a much higher abundance of primordial black holes from the get-go. Their formation isn't just a possibility, it could have been a rampant common process, flooding the young cosmos with these gravitational objects. Furthermore, the properties of these higher dimensional black holes would be bizarre and distinctive. A black hole formed when extra dimensions were relevant wouldn't be the simple, spherical object described by Karl Schwarzschild's solution. Its structure would be shaped by the geometry of the extra dimensions. In the first instance of its life, it might appear as a higher dimensional object, often modeled as a black string or a multi-dimensional hypersphere. As the universe expanded and cooled, the extra dimensions would have compactified, forcing this exotic black hole to shed its higher dimensional structure and settle down into the four-dimensional black holes we're familiar with. This transition itself could release a burst of energy or produce a specific gravitational wave signature, a relic echo of the higher dimensional past. But perhaps the most dramatic difference is in how these black holes would die. Hawking radiation, the process that makes black holes evaporate, is directly tied to the black hole's temperature, which depends on the strength of gravity at the horizon. In a higher dimensional scenario, the physics changes completely. Because gravity is stronger at small scales, a micro black hole has a much larger effective horizon radius in the higher dimensional bulk than it would appear to have in our three-dimensional brain. This larger horizon area means it can radiate away its energy much more efficiently. A primordial black hole in a universe with large extra dimensions would evaporate at a vastly accelerated rate, blazing through its life cycle in a fraction of the time it would take in a standard four-dimensional cosmos. A black hole that might have lived for billions of years could instead vanish in a spectacular flash just moments after the Big Bang. This radically altered evaporation timeline has two crucial implications. First, it means that any population of small primordial black holes created in these models would have evaporated extremely early, leaving behind a specific set of relics. They could have produced a deluge of exotic particles, distorted the cosmic microwave background in a unique way, or even reheated the universe, leaving an imprint that future observatories might detect. Second, it opens up a new window for their creation, not just in the past, but potentially in the present. If gravity becomes strong enough in extra-dimensional models, it's conceivable that the ultra-high-energy collisions produced in particle accelerators like the Large Hadron Collider could, for a fleeting instant, create a micro-black hole. This microscopic singularity would evaporate instantly via Hawking radiation, emitting a jet of particles that would be an unmistakable sign of new physics. While no such event has been detected yet, it remains a thrilling possibility that turns our largest machines into hunters for the deepest secrets of spacetime. Therefore, the search for primordial black holes is inextricably linked to the quest for a unified theory of physics. Finding evidence for them, and particularly measuring their abundance and mass distribution, wouldn't just tell us about the early universe, it would provide indirect but powerful evidence for the existence of extra dimensions. A confirmed detection of a large number of black holes in a mass range that standard inflation struggles to produce would be a strong hint that gravity played by different rules at the beginning of everything. These ancient objects could be the ultimate messengers from a higher dimensional epoch, their very existence a testament to a reality far grander and more hidden than we ever imagined, written in the language of gravity and woven into the fabric of the cosmos itself. Deep within the heart of our own galaxy, a mysterious and persistent glow has puzzled astronomers for over a decade. The Fermi Gamma Ray Space Telescope, meticulously mapping the sky, has detected a significant and unexpected excess of high-energy gamma rays emanating from the center of the Milky Way. This signal doesn't neatly align with any known population of pulsars or other stellar objects, leaving a tantalizing gap in our understanding. One of the most compelling proposals to explain this galactic center excess doesn't involve ordinary matter at all, but instead points to the annihilations of dark matter particles. However, if that dark matter is composed of primordial black holes, the explanation takes on an entirely new and fascinating layer, transforming these ancient objects from passive gravitational anchors into active destructive powerhouses. The standard dark matter annihilation model suggests that if dark matter is made of weakly interacting massive particles, or WIMP, then where the dark matter is most densely packed, these particles could occasionally collide and annihilate each other, converting their mass directly into energy and producing a spray of gamma rays. The galactic center, with its incredibly deep gravitational well, is predicted to have the highest density of dark matter in the entire galaxy, making it the prime hunting ground for such a signal. The Fermi excess has a spatial distribution and energy spectrum that some theorists argue is a good match for WIMP of a specific mass annihilating with one another. But this model has its challenges, particularly in explaining the exact brightness and shape of the signal without fine-tuning the properties of the hypothetical dark matter particle. This is where a hybrid model featuring primordial black holes offers a more dynamic and compelling narrative. Imagine a vast population of these ancient black holes forged in the Big Bang and now swarming through the galaxy's halo. Over billions of years, their orbits would have decayed, and they would have gradually migrated inward, dragged by dynamical friction and drawn by the immense gravity of the supermassive black hole, Sagittarius, a star that resides at the very center. This process would have led to a dramatic concentration of primordial black holes in the inner few light-years of the galaxy, creating a dense cluster of these invisible gravitational points. In this scenario, the black holes themselves are not annihilating, they are acting as powerful catalysts. Each primordial black hole would have a sphere of gravitational influence, and if dark matter particles exist, whether they are WIMP, actions, or something else, they would be captured by this gravity, forming an incredibly dense and swirling halo around each individual black hole. Think of it like a planet having an atmosphere, but this atmosphere is made of dark matter, and it's drawn from the surrounding galactic halo. The density of dark matter in these miniature halos could be many orders of magnitude higher than the average density in the general galactic center region. This intense concentration is the key to the entire process. When the density of dark matter becomes this high, the rate of particle collisions skyrockets. It's the difference between having a few people scattered across a large field and packing a huge crowd into a small room. The chances of them bumping into each other are vastly increased. Within these ultra-dense dark matter halos, the probability of annihilation events would be significantly enhanced. Each annihilation would produce its characteristic burst of gamma rays. Now multiply that by thousands or even millions of primordial black holes, each with its own annihilating dark matter halo, all clustered in the same central region of the galaxy. The collective signal from this immense ensemble could perfectly account for the smooth, large-scale gamma ray excess that Fermi observes, without requiring an unnaturally high rate of annihilation for the background dark matter elsewhere. This model elegantly solves several problems at once. First, it naturally explains why the excess is so centrally concentrated. That's where the black holes have gathered. Second, it provides a physical mechanism for achieving the necessary dark matter density to produce the observed signal. The gravitational pull of the black holes does the work of concentrating the particles. Finally, it offers a potential link between two great cosmic mysteries: the nature of dark matter and the existence of primordial black holes. The gamma rays from the galactic center would not be a direct signal of one or the other, but a signature of their symbiotic interaction, a testament to how these gravitational ghosts can shape and amplify the processes happening in the darkest corners of our galaxy. But the story of quantum entanglement and black holes ventures far beyond the paradox itself, opening up a breathtaking experimental possibility. If a significant number of small, ancient black holes do exist, they could serve as nature's own pre-built laboratories for testing quantum mechanics in the most extreme gravitational environments imaginable. This idea transforms them from theoretical puzzles into potential tools, offering a way to probe the mysterious interface where gravity meets the quantum world, a frontier that has eluded physicists for a century. The core of this proposal involves using the primordial black hole's immense gravity to stress test one of quantum mechanics' strangest and most robust phenomena: entanglement itself. Entanglement is a powerful connection that can form between two particles, where their properties become linked regardless of the distance separating them. Measuring the state of one particle instantly determines the state of its partner, a phenomenon that Albert Einstein famously dismissed as spooky action at a distance. Countless experiments have confirmed that entanglement is real, but all of these tests have been conducted in environments where gravity is negligible, on Earth or in satellites in low orbit where space-time is essentially flat. We have no experimental data on how this spooky connection behaves when one of the entangled particles is subjected to the kind of intense, warped gravity found at the edge of a black hole. A primordial black hole, especially a small, hot one, provides the perfect natural experiment. Imagine a carefully prepared pair of entangled particles. Using a futuristic spacecraft or a powerful laser, we could send one of the particles on a trajectory that takes it extremely close to the black hole's event horizon, while its partner remains safely far away in flat space. The particle near the black hole would experience severe time dilation and gravitational redshift effects predicted by general relativity. Its clock would tick infinitely slowly from our perspective, and the frequency of its quantum signals would be dramatically shifted. The question is, what happens to the entanglement? Does the intense gravity break the quantum connection, or does the entanglement persist, somehow adapting to the wildly different reference frames of the two particles? Different theories of quantum gravity make different predictions. Some models suggest that the extreme environment would cause the entanglement to decohere, effectively severing the spooky link. Others propose that the entanglement would be preserved, but the correlation between the particles would become scrambled in a very specific, measurable way. By comparing the measurements of the two particles after this gravitational ordeal, we could see which prediction holds true, gathering the first hard data on how gravity mediates its influence over quantum information. This isn't just about observing whether entanglement survives, it's about reading the specific signature of that survival. The way the quantum information is altered or preserved could act like a fingerprint, revealing the underlying mechanism that reconciles Einstein's smooth, geometric spacetime with the fuzzy, probabilistic world of quantum particles. A primordial black hole acts as the ultimate stressor, amplifying these subtle effects to a level we might finally be able to detect. It offers a natural, ultra-high-energy experiment that we could never hope to replicate in any particle accelerator on Earth, giving us a front-row seat to physics at the Planck scale. While the case for primordial black holes is compelling, a truly scientific perspective demands we also listen to the voices of caution. Not every anomalous signal in the cosmos is a footprint of an ancient gravitational ghost. Before we rewrite the textbooks, we must rigorously consider the more mundane explanations, the celestial imposters that could be masquerading as these exotic objects. This critical counterpoint is not a dismissal of the idea, but an essential part of the scientific process, ensuring that our excitement doesn't outpace the evidence. One of the most prominent alternative explanations takes aim at the very heart of the dark matter debate. The microlensing events that initially sparked the macho controversy, and which could be reinterpreted as evidence for primordial black holes, have a host of potential culprits. The galactic halo is not empty, it is likely filled with a vast number of faint, ordinary objects that are notoriously difficult to detect. Rogue planets hurled from their star systems by gravitational interactions could be incredibly common. These cold, dark worlds wandering in the interstellar void would produce microlensing signals identical to those of a black hole of the same mass. Similarly, brown dwarfs, failed stars too small to ignite sustained fusion, are another populous class of invisible object. Even the remnants of dead stars like cold white dwarfs and neutron stars that have faded to black over billions of years could account for a number of these lensing events. The challenge is that gravity is an impersonal force. It doesn't care if the mass causing the lensing is a planet, a dead star, or a primordial black hole. The light curve looks the same. The plot thickens when we consider the dynamic environment of the galactic center, a region teeming with energetic and poorly understood phenomena. The Fermi gamma-ray excess, which some models attribute to dark matter annihilation enhanced by primordial black holes, could have far more prosaic origins. Astronomers have proposed that a previously undetected population of millisecond pulsars could be the true source. These are rapidly spinning neutron stars that emit powerful, lighthouse-like beams of radiation, including gamma rays. Thousands of these faint, point-like sources clustered in the galactic center could blend together into a smooth, diffuse glow that mimics the expected signal from dark matter annihilation. Distinguishing between these two possibilities is a major focus of current research, requiring telescopes with ever greater resolution to pick apart the fuzzy gamma ray haze into its individual components. Even the most dramatic signals, like fast radio bursts, have compelling alternative theories that don't require black hole collisions. The leading explanation for many of these events points to magnetars, a specific type of neutron star with a magnetic field so powerful it could strip information from a credit card 100,000 kilometers away. These stars are known to undergo starquake sudden ruptures in their incredibly rigid crust, which can trigger massive, explosive releases of energy in the form of radio waves. A single, colossal starquake could easily produce a non-repeating fast radio burst with all the power and brevity we observe. This model is supported by the fact that we have detected a fast radio burst from a magnetar within our own galaxy, providing a direct link between the phenomenon and a known astrophysical object. Furthermore, we must always contend with the specter of instrumental artifacts. The data from our most advanced observatories is incredibly complex and requires sophisticated algorithms to process and interpret. A subtle glitch in a detector, an unaccounted-for source of background noise, or a statistical fluke in the analysis can sometimes produce a signal that looks tantalizingly real. The history of science is littered with such false positives, from the initial excitement over the supposed discovery of cosmic strings in the CMB to anomalous signals in particle detectors that later vanished with more data. This is not a failure of science, but its strength the built-in skepticism and relentless verification that slowly, painstakingly, separates true discovery from wishful thinking. This rigorous balancing act is what gives scientific discoveries their weight. The potential existence of primordial black holes is not diminished by these alternative explanations. Instead, their potential confirmation is made stronger by the process of systematically eliminating every other possibility. The ongoing debate forces theorists to sharpen their models and make more precise, testable predictions. It drives observers to build better instruments and develop more robust methods of analysis. By holding the extraordinary claim of primordial black holes to the highest standard of evidence, we ensure that if they are finally confirmed, their discovery will be unshakable, a true milestone in our understanding of the universe's hidden architecture. But perhaps the most audacious and speculative idea of all proposes that these ancient objects are not just participants in the cosmos, but could be fundamental to the very fabric of consciousness itself. This theory ventures far beyond conventional physics, weaving together cosmology, information theory, and some of the most profound questions about the nature of awareness. At its core is a radical proposition that the universe is not just a collection of matter and energy, but a vast, interconnected network of information processing. And within this model, the smallest primordial black holes could play a role far more sophisticated than we ever imagined, acting as natural nodes in a cosmic web of computation. The foundation of this idea rests on the work of theorists like Roger Penrose, who has long argued that consciousness may not be a product of classical computation, but rather a quantum gravitational phenomenon. In his Orch-or theory, Penrose suggests that the mysterious collapse of the quantum wave function the moment a probability becomes a definite reality is not random, but an objective process linked to the curvature of spacetime itself. This collapse is proposed to occur in structures within the brain called microtubules, and it is this orchestrated objective reduction that gives rise to moments of conscious awareness. It's a controversial idea, but it opens a fascinating door. If consciousness is intimately tied to the fundamental geometry of space-time, then the places where that geometry is most extreme, black holes, must be central to the conversation. This is where micro-primordial black holes enter the picture. A black hole, according to the holographic principle, is the ultimate information processor. All the information that falls into it is not lost but is encoded on its two-dimensional event horizon. The interior remains a mystery, but from the outside it acts as a kind of cosmic hard drive. Now imagine a universe permeated by a sea of these ultra-small, ultra-fast black holes, each one a self-contained unit processing quantum information at the Planck scale. In certain speculative cosmological models, this background hum of information processing isn't just noise. It could be the substrate upon which a larger cosmic consciousness is built. These black holes wouldn't be thinking in any human sense, but their constant activity of absorbing, storing, and potentially re-emitting information via Hawking radiation could form a fundamental layer of reality upon which more complex phenomena emerge. Some models even go a step further, proposing that our own universe could be a simulation running on an unfathomably powerful computer. If that were the case, it would need a physical substrate to process the information of every particle and force. What better hardware for such a task than a network of primordial black holes? Their incredible density and the way they naturally manage information according to the laws of quantum mechanics make them ideal candidates for the universe's processing units. In this mind-bending scenario, the galaxy itself, threaded with these ancient computational nodes, becomes a kind of cosmic brain, and the large-scale structure of the universe, the great cosmic web of galaxies and clusters, mirrors the neural networks of a biological brain. The connections are metaphorical, but they are mathematically suggestive, pointing to a deep and possibly fundamental link between the structure of the cosmos and the structure of thought. Of course, this remains one of the most speculative frontiers of theoretical physics and cosmology, a place where hard science blends with profound philosophy. There is no direct evidence for such a connection, and many scientists remain deeply skeptical, viewing it as a fascinating but untestable metaphor. Yet it serves a powerful purpose. It pushes our imagination to its absolute limits, forcing us to consider the universe not as a cold, mechanical clockwork, but as a dynamic, informed, and perhaps even aware system. Whether these ideas ever find experimental support, they remind us that the quest to understand primordial black holes is about much more than finding missing mass. It is a journey to the very edge of understanding, where gravity, information, and the nature of existence itself become inextricably linked. This brings us to one of the most profound implications of Hawking's work, a concept that challenges our very understanding of reality, the information paradox. When we think about a black hole, we picture an object defined by three simple properties: mass, spin, and charge. According to classical general relativity, if you were to throw a perfectly crafted grandfather clock, a burning library, and a container of hydrogen gas into a black hole, the result would be identical. All the intricate information about those objects, the clock's gears, the words in the books, the atomic states, would be irretrievably lost, erased from the universe. The black hole would simply get a little heavier and spin a bit faster, offering no clue about its dietary history. This presents a catastrophic problem for quantum mechanics, which is built on the unshakable principle that information can never be truly destroyed. It can be scrambled, hidden, and become impossibly complex to retrieve, but it must always, in principle, be preserved. The complete evaporation of a black hole via Hawking radiation seems to violate this rule spectacularly. After the black hole has vanished, leaving behind only a faint thermal glow, what happened to the information about the clock, the books, and the gas? If it's truly gone, then the foundational laws of quantum physics are wrong. This paradox has divided physicists for decades, but primordial black holes, especially the light ones that evaporate quickly, could be the key to resolving it, acting as natural laboratories for the universe's most extreme information processing. The most promising resolution to this paradox emerges from a revolutionary idea called the holographic principle. This concept suggests that all the information describing a three-dimensional volume of space, everything that happens inside it, can be entirely encoded on its two-dimensional boundary, much like a hologram on a credit card where a flat surface creates the illusion of depth. For a black hole, this means every single bit of information about everything that ever fell into it is not lost inside the singularity, but is instead perfectly preserved on its event horizon, the ultimate cosmic scratchpad. The AD/S/CFT correspondence, a specific realization of this principle, provides a powerful mathematical framework for this, proposing a perfect duality between a gravitational theory in a volume of space and a quantum field theory without gravity living on its boundary. This is where the evaporation of a primordial black hole becomes a potential goldmine for experimental physics. According to the holographic principle, as the black hole radiates, the information trapped on its surface must somehow be transferred to the outgoing Hawking radiation. It wouldn't be a clean, easy-to-read transfer. The information would be scrambled, chaotic, and encrypted in the subtle correlations between particles emitted at different times. The radiation would appear random and thermal only if you examine each particle in isolation. But if you could analyze the entire pattern of radiation over the black hole's complete lifetime, the full story of its contents should, in theory, be imprinted there. The final, explosive moments of an evaporating primordial black hole would be the grand decryption event, where the last of this scrambled information is blasted out into the universe. Detecting this would be the ultimate test. If we could ever observe the death of one of these ancient objects, we wouldn't just look for a flash of gamma rays. We would need to perform a full spectral analysis of that final burst, searching for tiny deviations from a perfect thermal blackbody spectrum. The telltale sign of information escape would be specific non-thermal correlations within the radiation statistical patterns that betray a hidden structure within the seemingly random spray of particles. Finding such a signature would be a monumental validation of the holographic principle and the AD/S/CFT correspondence, providing the first experimental evidence that our universe truly operates like a hologram, with the fabric of reality itself being a projection from a distant two-dimensional surface. Even more intriguing is the possibility of stable remnants. Some theories suggest that instead of evaporating completely, a black hole might shrink down to a plank-sized nugget, a stable relic that contains the entire information archive of the black hole's history. This infinitesimal object would be a frozen record of everything it ever consumed. If primordial black holes are abundant and leave behind such remnants, they could themselves constitute the dark matter, their collective gravitational pull shaped by the information they safeguard. The hunt for the holographic principle's signature is therefore not just about watching black holes die. It's about searching for the fundamental language of the universe, written in the final breath of its oldest and most mysterious inhabitants. Yet within the serene stability of our universe's vacuum state, a profound and unsettling possibility exists that this might not be the lowest possible energy level, that a truer, deeper vacuum could be waiting. If such a lower energy vacuum exists, a bubble of it could spontaneously form and expand at the speed of light, rewriting the fundamental laws of physics in its wake. This process, known as vacuum decay, would be the ultimate cosmic catastrophe, an irreversible event that would obliterate everything we know. The terrifying beauty of this idea is that it might not require a random quantum fluctuation to begin. It could be triggered or catalyzed by the most extreme objects in existence. This brings us to a theory where primordial black holes are not just relics, but potential agents of cosmic transformation, acting as natural lighters capable of igniting a fire that could consume the entire universe. To understand how this could happen, we need to picture the universe's vacuum not as true nothingness, but as a field brimming with potential energy, like a ball resting in a valley. Our universe is in a false vacuum, a valley that seems stable but actually sits on the slope of a much deeper, more stable valley, the true vacuum. For the ball to roll into that deeper valley, it needs to overcome an energy barrier, a hill separating the two states. This usually requires a tremendous, unlikely quantum fluctuation. But a primordial black hole could provide a shortcut. Its immense gravity creates such a powerful warp in space-time that it effectively lowers the energy barrier surrounding the true vacuum. In the incredibly curved space right at the edge of its event horizon, the probability of a quantum tunneling event, a jump into the lower energy state, could be dramatically increased. The black hole acts like a thorn piercing the fabric of space-time, a weak point where the vacuum's stability is compromised. If this catalyzed decay were to occur, the black hole would become the nucleation site for a bubble of true vacuum. This bubble would then expand outward at the speed of light, its boundary a wall of incalculable energy. As it expands, it would not destroy matter in a conventional sense, it would dismantle reality itself. The fundamental constants we rely on, the masses of particles, the strength of forces, would be rewritten to new values within the bubble. Atoms could not hold together, chemistry would cease to function, and the universe as we know it would simply stop existing, replaced by a new reality with entirely different and likely inhospitable physical laws. The primordial black hole, a fossil from the first moment, could therefore be the seed for the last moment of the cosmos we recognize. Now, the immediate existential question is whether this is happening right now or could happen. The reassuring answer is that if our universe's vacuum is metastable, its predicted lifetime is astronomically long, far exceeding the current age of the universe. The probability of a random fluctuation causing decay is vanishingly small. However, the presence of a catalyst like a primordial black hole changes that calculation. It localizes the risk, concentrating it around these specific gravitational anomalies. The risk would be greatest for the smallest black holes, as their higher temperatures and more intense Hawking radiation could provide the additional energy needed to push the vacuum over the edge. If a population of these tiny, hot, evaporating black holes exists, each one could be a potential trigger. Thankfully, if such a decay event were to occur anywhere in the observable universe, we would have no warning. The wall of the new vacuum would arrive at the speed of light, and our understanding of physics would end in the same instant we detected it. This theory, while deeply speculative, transforms our perspective on these ancient objects. They are no longer just potential dark matter or galactic seeds. They become existential signposts. Their existence and properties could tell us whether our universe is sitting in a comfortably stable state or precariously perched on a slope, with countless invisible triggers scattered throughout the galaxy. The search for them and the study of vacuum stability is therefore not just an academic exercise. It is a fundamental inquiry into the long-term fate of all reality, a question of whether the cosmos is inherently stable or if its deepest architecture contains the seeds of its own eventual transformation. While the standard picture of cosmic inflation involves a single field rolling slowly down a potential energy hill, this is far from the only possibility. The universe's initial explosive growth might have been a much more complex and dynamic affair, involving multiple fields, different types of energy, and even modifications to the very laws that govern quantum fluctuations. Intriguingly, the specific ways primordial black holes could have formed provide a unique testing ground for these alternative inflation models, offering a potential bridge between abstract theory and observable reality. Consider the concept of warm inflation. In the standard, cold inflation model, the inflattened field is isolated, driving expansion in a supercooled universe with virtually no interaction with other particles or radiation. Warm inflation proposes a radically different environment, where the inflaton field is strongly coupled to other quantum fields throughout the inflationary period. This interaction causes the inflaton to dissipate its energy, continuously producing a thermal bath of radiation that coexists with the inflationary expansion itself. It's not a cold, empty expansion, but a warm, seething one. This constant production of radiation has a direct and dramatic impact on the formation of primordial black holes. The quantum fluctuations that are stretched to become density perturbations are no longer born in a vacuum. They emerge within a hot thermal environment. This thermal noise can actually amplify the fluctuations, making large black hole forming over densities much more likely than in cold inflation. Furthermore, the physics of how these fluctuations evolve is changed. In cold inflation, perturbations are essentially frozen until after inflation ends. In warm inflation, the presence of radiation provides a damping effect, altering their growth and potentially producing a very specific, non-Gaussian distribution of fluctuation sizes. A confirmed detection of a primordial black hole population with a particular mass spectrum could therefore be interpreted as strong evidence that the universe's infancy was not cold and lonely, but was instead a warm and interactive process from the very beginning. Another fascinating alternative involves tinkering with the fundamental relationship between energy and momentum for the inflaton field itself, known as its dispersion relation. In standard physics, this relation is linear, but some theories of quantum gravity suggest that at the incredibly high energies of inflation, it could become non-linear. Imagine the inflaton field not as a smooth wave, but as a field with a strange, new kind of turbulence dictated by a higher power law. This modification would profoundly change the behavior of the quantum fluctuations it generates. A modified dispersion relation can act like a cosmic filter, selectively amplifying fluctuations at certain scales. For a standard linear relation, the power spectrum of fluctuations is nearly scale invariant, meaning all scales are perturbed roughly equally. But with a non-linear relation, you can get a powerful and sharp spike in the power at one very specific wavelength. This is a prime recipe for making primordial black holes. Instead of a smooth distribution of black hole masses, such a model would predict a very narrow, monochromatic spectrum. If astronomers were to discover that the cosmos contains a vast number of primordial black holes, all with almost exactly the same mass, say, all around the mass of a large asteroid, it would be a stunningly precise fingerprint of this kind of physics operating during inflation. It would tell us that the rules of the game were different at the highest energies, providing a direct glimpse into the realm of quantum gravity. These alternative models do more than just offer different pathways to black hole formation. They make distinct and testable predictions that differentiate them from the standard paradigm. The mass distribution of the resulting black holes is the key signature. Did they form from a broad spectrum of density fluctuations, suggesting a standard cold inflationary role? Or do we see a very narrow peak in their masses, pointing to a resonant enhancement from a feature in the inflationary potential or a modified dispersion relation? Does their abundance suggest they were born in a thermal bath, as warm inflation would predict? The answers to these questions, gleaned from future observational campaigns, will allow us to effectively rule in or rule out entire classes of inflationary models. The search for these ancient gravitational fossils is therefore not just a hunt for dark matter or exotic objects. It is a direct archaeological dig into the physics of the universe's first trillionth of a second, a way to read the hidden blueprint of inflation itself. But perhaps the most audacious and speculative idea of all proposes that these ancient objects are not just participants in the cosmos, but could be fundamental to the very fabric of consciousness itself. This theory ventures far beyond conventional physics, weaving together cosmology, information theory, and some of the most profound questions about the nature of awareness. At its core is a radical proposition that the universe is not just a collection of matter and energy, but a vast, interconnected network of information processing. And within this model, the smallest primordial black holes could play a role far more sophisticated than we ever imagined, acting as natural nodes in a cosmic web of computation. The foundation of this idea rests on the work of theorists like Roger Penrose, who has long argued that consciousness may not be a product of classical computation, but rather a quantum gravitational phenomenon. In his Or theory, Penrose suggests that the mysterious collapse of the quantum wave function the moment a probability becomes a definite reality is not random, but an objective process linked to the curvature of spacetime itself. This collapse is proposed to occur in structures within the brain called microtubules, and it is this orchestrated objective reduction that gives rise to moments of conscious awareness. It's a controversial idea, but it opens a fascinating door. If consciousness is intimately tied to the fundamental geometry of spacetime, then the places where that geometry is most extreme, black holes, must be central to the conversation. This is where micro-primordial black holes enter the picture. A black hole, according to the holographic principle, is the ultimate information processor. All the information that falls into it is not lost but is encoded on its two-dimensional event horizon. The interior remains a mystery, but from the outside it acts as a kind of cosmic hard drive. Now imagine a universe permeated by a sea of these ultra-small, ultra-fast black holes, each one a self-contained unit processing quantum information at the Planck scale. In certain speculative cosmological models, this background hum of information processing isn't just noise. It could be the substrate upon which a larger cosmic consciousness is built. These black holes wouldn't be thinking in any human sense, but their constant activity of absorbing, storing, and potentially re-emitting information via Hawking radiation could form a fundamental layer of reality upon which more complex phenomena emerge. Some models even go a step further, proposing that our own universe could be a simulation running on an unfathomably powerful computer. If that were the case, it would need a physical substrate to process the information of every particle and force. What better hardware for such a task than a network of primordial black holes? Their incredible density and the way they naturally manage information according to the laws of quantum mechanics make them ideal candidates for the universe's processing units. In this mind-bending scenario, the galaxy itself, threaded with these ancient computational nodes, becomes a kind of cosmic brain, and the large-scale structure of the universe, the great cosmic web of galaxies and clusters, mirrors the neural networks of a biological brain. The connections are metaphorical, but they are mathematically suggestive, pointing to a deep and possibly fundamental link between the structure of the cosmos and the structure of thought. Of course, this remains one of the most speculative frontiers of theoretical physics and cosmology, a place where hard science blends with profound philosophy. There is no direct evidence for such a connection, and many scientists remain deeply skeptical, viewing it as a fascinating but untestable metaphor. Yet, it serves a powerful purpose. It pushes our imagination to its absolute limits, forcing us to consider the universe not as a cold, mechanical clockwork, but as a dynamic, informed, and perhaps even aware system. Whether these ideas ever find experimental support, they remind us that the quest to understand primordial black holes is about much more than finding missing mass. It is a journey to the very edge of understanding, where gravity, information, and the nature of existence itself become inextricably linked. For all their theoretical promise, the ultimate proof of primordial black holes lies not in our equations, but in our ability to actually find them. The hunt is accelerating, moving from speculative searches to sophisticated, multi-pronged observational campaigns that leverage the most advanced technology humanity can muster. The next generation of telescopes and detectors, both on the ground and in space, are being designed with these cosmic ghosts squarely in their sights, offering our best chance yet to move from theory to discovery. The realm of gravitational wave astronomy is poised for a revolution that could crack the case wide open. Ground-based observatories like LIGO and Virgo have given us our first glimpses of black hole mergers, but their sensitivity is limited to frequencies that correspond to stellar mass objects. To hear the whispers of much smaller or vastly larger black holes, we need to go to space. The Laser Interferometer Space Antenna, or LISA, is a monumental mission led by the European Space Agency with NASA participation, planned for launch in the 2030. This will consist of 3 spacecraft flying in a vast triangular formation, trailing Earth in its orbit around the Sun. With arms millions of kilometers long, LISA will be sensitive to gravitational waves at much lower frequencies, opening a completely new window onto the cosmos. This low-frequency band is where the music of the early universe plays. LISA could detect the mergers of primordial black holes with masses ranging from a few hundred to several 100,000 times that of our Sun. If a population of these intermediate mass black holes exists, their slow, stately inspiral and merger will create a gravitational wave chorus that LISA is perfectly tuned to hear. Furthermore, if a primordial black hole were to be captured by a supermassive black hole at the center of a galaxy, a process known as an extreme mass ratio inspiral, LISA would not only detect it but provide exquisitely precise measurements of the smaller object's mass and spin, potentially confirming its ancient non-stellar origin. The data from this one mission could single-handedly confirm or rule out entire classes of primordial black hole models. Back on Earth, the search through gravitational lensing is entering a new era of unprecedented scale and precision. The Vera C. Rubin Observatory's legacy survey of space and time will be a game-changer. Starting in the next few years, this immense project will scan the entire visible southern sky every few nights for a decade, creating an unimaginably vast movie of the cosmos. It will monitor billions of stars, and in doing so, it will catch countless microlensing events. The sheer volume of data will allow astronomers to perform incredibly sensitive statistical analyses, searching for the telltale brief brightening that signals the passage of an invisible object. The survey's power lies in its ability to detect events from black holes across a wide mass range, from planetary masses all the way up to the stellar scale. It will be sensitive enough to potentially find the predicted population of asteroid mass black holes, whose lensing events would be too fleeting for previous surveys to catch. By mapping the number, duration, and distribution of these events, the Rubin Observatory will build a definitive census of compact objects in our galactic halo, finally revealing what fraction of the dark matter, if any, is made of primordial black holes. The power of these searches is magnified 1,000-fold when combined with the principles of multi-messenger astronomy, the practice of observing cosmic events using different signals like light, gravitational waves, and neutrinos simultaneously. Imagine a scenario where a microlensing survey detects the characteristic brightening of a star, indicating the passage of a compact object. If, at that exact moment, a gravitational wave detector like LIGO or Virgo also picks up a signal from the same patch of sky, it would be the smoking gun. The lensing event would tell us the object's mass through the duration of the brightening, while the gravitational wave signal could reveal its unique in-spiral signature and spin. This cross-correlation would provide a complete identification, distinguishing a primordial black hole from a more mundane object like a faint star or a rogue planet with absolute certainty. This coordinated approach turns our separate observatories into a single, unified instrument for decoding the universe's darkest secrets. Even the oldest light in the universe, the cosmic microwave background, will be re-examined with powerful new tools. Future CMB experiments like the Simons Observatory and the proposed CMB S4 project will map the temperature and polarization of this afterglow with razor-sharp resolution and incredible sensitivity. These maps will be scoured for 2 key signatures: The first is the subtle distortion caused by the collective gravitational lensing of a widespread population of massive primordial black holes. The second, even more subtle, is the unique polarization pattern that could be imprinted by gravitational waves themselves, generated in the early universe during periods of intense black hole formation. These primordial gravitational waves would be a fossil record of the universe's most violent initial moments, and their detection would provide indirect but powerful evidence for the mechanisms that could have created these ancient objects. The hunt is truly becoming a full-spectrum endeavor, engaging every tool at our disposal, from the precise timing of pulsars that can be perturbed by passing black holes to the potential detection of their Hawking radiation evaporation bursts by next-generation gamma-ray and radio telescopes. The net is closing. Each null result helps to further constrain the possibilities, carving away at the parameter space where these elusive objects could still be hiding. And a positive detection from any one of these methods would send shockwaves through the world of physics, finally providing a tangible piece of the cosmic dawn and irrevocably changing our understanding of what the universe is made of. We have journeyed through 30 incredible theories from the birth of the cosmos to the edge of theoretical physics, and what emerges is a breathtaking possibility that the universe's darkest secrets are not locked away in undiscovered particles, but in ancient gravitational fossils woven into the fabric of spacetime itself. Primordial black holes stand as a potential master key, capable of unlocking mysteries that have defined modern science. They could be the invisible dark matter binding galaxies together, the massive seeds that grew into the supermassive black hearts of galaxies far sooner than should have been possible, and the cosmic architects responsible for the very matter that makes up our world. They might even serve as our first experimental portal into the quantum nature of gravity, offering a front-row seat to the evaporation process that could finally resolve the information paradox and reveal if our universe truly operates like a hologram. The profound implications stretch across every domain of physics. For cosmology, their discovery would be a direct window into the conditions of the Big Bang, validating or refuting our most ambitious models of cosmic inflation. For particle physics, they could render decades of searching for WIMP obsolete, replacing a sea of invisible particles with macroscopic, gravity-only objects. And for quantum gravity, an evaporating primordial black hole is a natural laboratory, its final explosive moments potentially encoding the unified laws of physics in its radiation spectrum. These objects force us to ask deeper questions about the fundamental constants of nature, the stability of our vacuum, and even the possibility that our universe is one bubble in a vast multiverse, with collisions between these realms leaving black holes as their only tangible evidence. This isn't just a theoretical playground, it's a detective story where the clues are written in gravity, light, and the deepest layers of cosmic history. The next decade of observation will be decisive. The Vera C. Rubin Observatory will scan the skies for their microlensing signatures. The LISA mission will listen for their low-frequency gravitational wave mergers, and ever more sensitive telescopes will hunt for the gamma-ray bursts of their explosive deaths. Each new dataset brings us closer to answering whether these cosmic ghosts are real. The hunt is on, and we are all witnesses to a potential revolution in our understanding of reality. Now we want to hear from you. Which of these 30 theories do you find most compelling? Do you believe dark matter is made of these ancient objects, or do you think their role in shaping the early universe is their most important function? Share your thoughts in the comments below and subscribe to join us as we continue to explore the greatest mysteries